dove la mettono?
Sul desktop. Voi su questo monitor potete fare qualsiasi cosa, tanto non va in streaming questo qua. Adesso vi faccio vedere.
Perché l'unica cosa che nessuno di loro gestisce sono il cambio di presentazione.
Domanda che non ho fatto. Nessun video c'ha l'audio, vero? No. Tutto senza audio. Allora lo disattiviamo. Così non facciamo danni. Sono qua queste 3 cartelle.
Ok, l'unica cosa, le puoi già lasciare aperte in barra o no?
Tutte?
Sì.
Di PowerPoint, poi sono mai che
no, perché poi lui prende e manda in streaming quello che si apre in PowerPoint.
Ok, va bene.
Quindi è meglio aprirlo uno per volta.
Va bene.
Vedi, adesso l'abbiamo aperta ma in streaming non ci sta andando.
Ci va quando vai in
F5, adesso sta andando in streaming.
E invece per uscire
lo vedi anche da qua.
Per uscire dallo streaming, quindi dall'F5 diciamo per tornare su un est normalissimo. E questo lo gestisco normalissimo. Una volta che io vado in est, scusa, non posso. E invece se tu ritorni qua, perfetto. Ok, giusto per i camera.
Comunque dicevo, qui dal programma vedete il ingresso dell'audio. Ok? Se volete dare un'occhiata, magari se volete stare. Diciamo che se state qui in zona. Diciamo che se state qui in zona computer è meglio. Perché il microfono è qua.
Ah, per parlare.
Il microfono è qua sopra.
Ma tanto se il mouse qua. L'unica cosa è che devono stare fuori dal. Diciamo, non essere.
Se stanno qua non lo impallano. Si girano il mouse da sta parte.
Come ti ho detto prima, state attenti a spostare il computer perché collegato al mondo.
A me è meglio di qua, perché non facciamo lista nessuno.
Ma il driver è troppo. Per sentirvi meglio.
Il microfono è qua sopra.
Ma anche così
sì, no, ma
guarda, se fanno silenzio dentro il microfono.
Anzi, tu adesso che stai parlando stai andando in
già da questo volume è
alto. Fai finta di presentare.
Io sto anche guardando la schermo.
Sì, va bene.
Cioè, non dovrai farlo, però se nei casi di giro sempre comunque bene fare.
Sì.
Non parlateci vicino, piuttosto, no?
Questo poi lo guardiamo da giù noi. Questo lo chiudo. Sì, sta andando.
Anche su YouTube?
Sì.
Mettiamo le voci.
Vediamo un attimo. No, volevo vedere un attimo la qualità che c'è su YouTube. La chiudo. E questo lasciatelo aperto. Non toccatelo. Sì.
Okay, so we can start our final presentation morning. First of all, thanks to everybody for being here. I just recall for those that are not experienced about this event that this is part of the exams that is called Precision Design. Last year course for Space Engineering Master here in Politecnico, and what you are going to see is the work done, like the feasibility studies that are done in the agencies, in the space agencies, 3 months almost work, according to a mission that has never been done. So it's a real new study, and the strategy and the process is like the concurrent design approach, with a lot of review and let's say interface among the specialists. All the students that you are going to see is part of a team, of course. Each of them are responsible for one of the subsystems all over the study. And there is a team leader that is also a system engineer for 2 weeks long along the whole course in order to learn how to, let's say, lead a group and manage a system design. I just tell you that this is the first time that we are also in streaming, so we are also on a YouTube channel in order to allow people that cannot attend at least to see the presentation. The agenda will be to have the Harmonia as the first mission to Mars with such a kind of balloons as you will see in a while. Then we will jump in the deep space with the Galaxy Ranger telescope, and then we end up with the lunar sample return, the Mozart mission. I propose to have the presentation and then a first time slot for question and answer, and then keep on going. Because of the schedule that is quite tight, I suggest not to have any break, but feel free to stand and have a coffee outside and come back. So it's really free. Do not stack on your chair, dying because of the hot place we are giving the presentation. So I leave the room to the guys and enjoy the day. And thanks for being here.
Good morning, everybody. I'm Marco Bevilacqua. I'm the team leader of Harmonia Group for this last period of the project. Harmonia name comes from the name of the daughter of Ares, since it's a mission on Mars, and also recalls such a concept of coordination between different subsystems, because our mission is quite complex. I will briefly talk about our mission, so a brief overview, and then let the word to my colleagues who will speak about the first mission analysis and then the different segments of our mission, and finally we conclude with the mass budget and power budget, risk analysis, and finally the conclusions. So, starting from the inputs that of our mission, we have to exploit aerial platforms on Mars atmosphere to perform in situ measurements to collect high-resolution data in Mars atmosphere, and also to deliver a distributed sensor on Mars surface to collect also seismological and other ground data. All this has to be done with some constraints. In particular, we have to visit peculiar regions like Valles Marineris and Hellas Planitia, and also the polar caps during the period of sublimation. All this trying to obtain an operative lifetime of at least 2 years, and some other constraints related to the launch date and the data relay. Looking more in details to the phenomena we are going to observe, we have divided them into three major regions. First, in the tropical region, we would like to observe the genesis of local dust storms, dust tables, other phenomena like the sources of methane. And in the polar region, where I would like to observe for sure polar cap sublimation, and again the source of methane. In addition, we would like to observe remotely the residual magnetic field of Mars. Our mission is based on mainly the use of 3 superpressure balloons as aerial segments. This is our choice. We decided to deliver them 2 in tropical region and 1 on the polar cap. This allows us to reach the 2 years operational lifetime, since the lifetime of single balloon is not sufficient to cover the whole mission. This is not done continuously, but at least they will cover the most relevant, scientifically relevant periods on Mars. We will also rely on dedicated entry vehicle, 1 entry vehicle for each balloon. Thus, we can inflate balloons directly in flight. This is the most, you can say, promising technique for inflating balloons. And but this will also allow us to have a sort of flexibility on the regional deployment of our balloons, and also in the time deployment of our balloons. We can deploy them directly on the regions we would like to visit without the need of guidance to reach the most peculiar regions. And we can also try to reschedule the mission if something goes wrong, for example. So it gives us robustness, flexibility, and adaptivity. We'll also will rely on an orbiter who will act as a balloon tracker, and will also collect data and send them to Earth. Finally, we will have 2 ground stations that will be released from the 2 tropical entry vehicles. They are quite massive, that's why they cannot be carried by the balloons, and that's the only, let's say, weak point with respect to the requirements we were given, because we were asked to have 4 ground stations, but that was not possible unless we let them be carried by the balloons. So having a quick look about the dimension on the dimension of our mission, we have a ground station which is in the order of less than 1 meter, a balloon that will be more than 30 meter. They are different, the tropical and the polar. The polar will be a bit smaller. The gondola which will be hanged behind the balloon, which will be in the order of 1.5 meters, and the overall segment composed by the orbiter and the entry vehicle attached in series will be in the order of meters. So finally, we will have also GEMS as a technological demonstration. GEMS are nanoscale sensors. They were first thought as an alternative to balloons, but then due to their limited lifetime and some telecommunication issues, they have been discarded and then reintroduced as a technological demonstration. They can be released by balloons in a peculiar period or during some relevant events. There are also representative models of the sensor. Having a look to the time scale of our mission, we will mainly have 3 phases. After the launch, we will have the transfer from Earth to Mars. Then we will have an aero break of about 150 days to save more or less propellant and make the mission feasible. And then we will have the 2 years of operational lifetime ending with the disposal. Having a look more in detail to the operation in the operational lifetime, we will have first a 1 month setup, which will be practically 1 month during which we will observe Mars and try to set up everything and maybe reschedule something or some kind of adaptive to the mission. Then we will have the 18 months of measurement campaign, during which there will be released the 3 balloons according to what we have decided. Finally, we will have also a buffer slot of 5 months to have further measurements, or if the balloons will survive for more than what expected, we can keep on collecting data, and also from the ground station we could keep on collecting data. We could also rely on the possible of releasing balloons in common periods to try to have simultaneous measurements. The balloons are scheduled according to scientifically relevant seasons. That's more or less all. I will leave the word to Amedeo Rocchi, who will talk about mission analysis.
Thank you. So, we started from the interplanetary transfer for the mission analysis, and we had as a driver, of course, the mass maximization at the Mars target orbit, and we had some constraint on the departure date, and we selected a direct transfer since it's the most used technique, and we assumed we used the Likert-Koenig model, and we assumed the chemical propulsion, so impulsive maneuvers. We produced, for example, this workshop, and we selected the best launch date that you can see here, which has a transfer time of 310 days. Here you can see the trajectory. There is nothing special to be said. For what concerns the insertion in the operational orbit, we considered first a direct transfer to the operational orbit with one-shot maneuver, and but this gave us a result at delta V of 2 km per second. But since we have a massive dry spacecraft and the delta V is quite high, no launcher is feasible, usable to launch such an high mass with a given C3 we have. So we need to reduce somehow the delta V required to insert ourselves in the operational orbit. What we selected was an aero braking maneuver. We selected that because it's flight proven twice at Mars. It doesn't prompt too much the interplanetary transfer. It doesn't have strong requirement in the configuration of the spacecraft, but leads to large delta V savings. So we used a simplified model for the simulation, and we neglected Mars rotation, and we assumed an exponential model for the atmosphere. And we selected some parameters. So the initial orbit, similar to the MRO mission, so with the apocenter just inside the sphere of influence of Mars, and the pericenter equal to the operational orbit we selected. During the aero braking regime, we will have a pericenter of about 100 kilometers, and this is what's chosen in order to minimize the duration and have acceptable thermal and structural loads. So this is the result we get. it's a delta V saving of 1.2 kilometers per second that lead to a huge mass reduction. And the possible issues were analyzed and solved because almost 5 months in order to to reach the operational orbit are okay in the mission timeline. And the thermal and structural loads were analyzed and were acceptable. Here you can see basically the initial orbit, the blue one, and then every 50 orbit here are represented in orbit, and as you can see the apocenter is decreasing up to reaching the operational orbit in green. So coming back to the launcher selection, this was the old value with a given C3 and the mass considering the delta V of 2 kilometers per second. And you can see that no launcher is available on the market to launch our spacecraft. But with our braking maneuver, we are feasible with the delta 4 heavy configuration, and this is the only option we have. For what concerns the operational orbit choice, we had as a driver the maximization of the time in view of the aerial and ground segment. So we took data from the simulation of the balloon motion, and we had some latitude ranges. They were taken into account. And we had some constraint on at least the possibility of deploying a balloon near the pole, and altitude of the pericenter not too high in order not to have too much drag and so too much station keeping delta V. So we have also some nice to have constraints. For example, a high coverage of Mars surface and a low altitude orbit in order to have better communication with the ground segment and the aerial segment, and to have a cheaper re-entry for the entry vehicles. Here you can see, of course, we use a trade-off in order to select the orbit because there is no other way. And here you can see the altitude of pericenter, the altitude of apocenter, the inclination, and the angle of perigee. You can see it is basically almost a circular trajectory and almost polar. Here are represented the trajectory in a Mars inertial reference frame for 12 orbital periods. And you can see here it's not a repeated orbit. So we maximize for the communication windows, and these are the results we get using simple formulas and numerical simulation. Assuming a minimum relation angle for the communication of 10 degrees. So we got a minimum communication window of 7.1 minutes per Martian day. And we have a 100% of coverage of Mars surface in 1 day, so no blind spot for the aerial and ground segments. This is just an example for one orbital period of the coverage. For what concerns the entry vehicles, we selected a procedure in order to release them, and it's the following. We acquire a release orbit slightly lower than the operational orbit. We release the entry vehicle and the related structure, as it will be explained later, and then we return to the operational orbit. For what concerns the trajectory of the entry vehicles themselves, we had as a driver, again, the delta V minimization. And we use a model for the orbital phase and the first order Allen model for the atmospheric phase. We had some constraint on the velocity at which the supersonic parachute will be released, and also concerning the flight path angle in order to minimize again the delta V and to keep the entry vehicle inside the atmosphere. And this is the parameter we selected, again with the trade-off. And this is the results we get. Here you can see an example of the three phases entry. So this is the release orbit. This is the orbital arc, and this is the ballistic arc, and this finally is the atmospheric descent. Here is an example for the Valles Marineris balloon, but they're also represented on the other two spots we're going to visit. Hellas Peninsula is on the other side of the planet. The trajectory can be defined simply by the true anomaly of their insertion starting from the operational orbit, and the release orbit. Finally, I will present the delta V budget, just the contribution I didn't highlight before. So we have to consider the trajectory correction maneuvers, the correction during the aerobraking regime in order to keep the altitude of the pericenter constant, the station tipping contribution, and the decommissioning also phase was considered. The delta V budget was also made for not only for the orbit but also for each of the entry vehicles. I will now leave the stage to Claudio Pulsi that will tell you all about the balloon design.
Thank you. I will try to explain the process that has brought us to the design of the balloons that supports the aerial platforms. And so first of all, an analysis phase during which we have studied the environment of Mars. We have selected the technology for the balloons, and we asked ourselves if we wanted to rely on a guidance navigation and control system on the platforms, and at last the strategy for the buoyancy of the balloon. Then a sizing phase during which we have decided to compute the dimension of the balloons. We have chosen the material for the envelope, and we have at last produced two numerical models as a validation of our design, a thermodynamic model and a flight dynamic model. So first of all, for the environment, we have used as a tool the Mars Climate Database from ESA that receives as inputs space and time coordinates on the surface of Mars and gives as outputs the main properties of the atmosphere, such as density, pressures, and etc. So, for example, for what concerns the thermal environment, we have analyzed the scattering phenomena due to the presence of the atmosphere, and here you can see we have analyzed in the 4 different seasons on Mars. You can see the equinoxes scenario here, and the northern and summer and southern summer on Mars, and correspondingly the launch windows of the balloon. For what concerns the technology that we have used, we have investigated through the existing technologies, but at the end we have selected the superpressure balloons because the superpressure balloon is actually a balloon that has a constant volume supported by an higher pressure inside the balloon with always greater than the environmental pressure, and flies at a constant density level. The positive aspects of this technology are that it has already been used in the Vega mission in 1995 on Venus. It has a longer lifetime with respect to the other technologies, and it has a simpler design because of the constant volume. And but let's say the negative aspects are related to the fact that since it has a constant volume, the buoyancy capabilities relies on the external density of the atmosphere. So gradient of density could cause a rapid change in altitude of the balloon, and the gas needed for inflation has to be brought from Earth to Mars. Helium in our case. For what concerns the guidance, navigation, and control system, actually this technology is already been investigated by NASA, and as a sort of a wing attached very far below from the balloons, in order to experience a different condition in the atmospheric properties, and to produce force that could direct the motion of the balloons. Of course, with this technology, we could have optimized the exploration capabilities of the balloons and also perform maybe maneuvers to avoid impacts from the orographic obstacles. But we will have also increased the complexity of our system, increase the mass, and also increase the dimension of the balloon, since the long tether needs, of course, a higher floating altitude. So we decided not to rely on GNC system, but rather on free motion of the balloons. So a proper design of the density, floating density of the balloon was needed. So, as I said, the superpressure balloon flies at a constant density level. So we have to choose the criteria, the density through some criteria. And we have created a model of isodensity surface in the atmosphere of Mars, and marked them with 2 performance indexes, such as the altitude experienced from the balloon. There has to be as much as low as possible in order to perform good quality measurements, but not too low in order to avoid the impact on the obstacle. So these that are the two performance indexes. So, for example, for the tropical balloon, we have made a compromise on the percentage of the orographic obstacles at at the density of this value, and an altitude that is low enough to properly do the scientific operations. And so, as you can see, we have also visible criteria to observe the result that we have got. So, for what concerns the balloon sizing, we have followed the static dimensioning through the Archimedes principle and exploited the two concepts on which the superpressure balloons technology is based, that are superheat and superpressure. The superheat is the delta temperature across the envelope of the balloon that must be inside the assumed values, and the superpressure, of course, is the delta pressure across the envelope that must be always greater than zero. And so, with that, those as inputs, we have come out with the actual sizing of the dimension of the balloon. For what concerns instead the material, we choose to rely on a composite envelope material in order to match all the requirements such as strength, stiffness, in particularly permeability of helium, because we wanted to increase the lifetime of the balloon. The UV resistance, that is a major concern on the atmosphere of Mars. And so we have selected 3-layer composite material, low density polyethylene on the external side, in the middle of a fiber spectra, and inside the mylar. Two design, one for the polar balloon and one for the two tropical balloons. And actually, the tropical balloons, as I said before, are bigger because they rely on a lower floating density. In order to validate the assumption on the superheat and super pressure, we have made a thermodynamic model of the balloon, considering all the thermal sources, including the internal reflection and transmission and convection natural inside of the balloon and forced outside, considering the winds. And we had to check the superheat delta temperature actually was always under the upper limit, and a super pressure higher than a lower limit. And we checked that design actually could work. As a last tool for the validation, we have made a solid dynamic model of the motion of the balloon, extracting from the mass climate database a mesh for the atmosphere of Mars that receives that for many points on the surface inside in the atmosphere and in time gives out as the information on the characteristics of the atmosphere. And we have simulated the vertical motion and the horizontal motion in order to understand if the correct altitude was reached, and also if actually the guided navigation and control issue was discarded for a good reason. We have also extracted from the simulation interesting results for the EPS subsystem, such as the sun elevation and simultaneous exposition of the balloons, for the thermal environment, for the thermal control system, and as I said, as Amadeo said before, the ground track formation analysis. And these are two examples of the motion of the balloon. Here you can see the starting point in the red dots, and this is the first launch from Hellas Planitia. And this is the second launch on the North Pole. You can see the balloon descending caused by the sublimation of the CO2 from the polar caps that creates the currents towards the air. And this actually helped us on discarding the GNC hypothesis, since we have seen that the balloons actually perform the required, let's say, motion. So now I leave the word to Vincenzo Pesce, that will talk about the payload of the balloon.
Good morning. We talk about the gondola, that is the core of the AMO segment. So you can see that we have to perform some analysis and to observe some phenomena such as the polar cap sublimation, thus the industrial formation. And for this reason, we have selected this kind of instruments that always have an high TRL except for the ultrasonic wind sensor, the micromima, that is a spectrometer that was developed here at PoliMI. Then going to detail, we have the gondola attached to the balloon with a 500 meter tether, as you can see also in the work. And this is mainly for the reason for avoiding the shadow of the balloon on the gondola itself, and because of communication, in order to allow communication between the gondola and the orbiter. Going to detail of the configuration, the main driver of the configuration is the power requirements, because we have to face the low irradiance levels present on Mars. So we have to have larger solar rays area in order to also to satisfy the constraint of the volume, the limited volume of the entry vehicle. We have decided to have a truncated pyramid with extendable body-mounted arrays. And so, going to detail of the configuration, we have this kind of electronic box with a radiator in the bottom part connected with its switches. Here we have the instrument, so the spectrometer, the UNICAP, and the ultrasonic wind sensor is attached to a deployable boom in order to not have any noise from the structure. Then we have the antenna, and then from this view we can see the gems, the jettisonable gems, and the camera. So a video where we can see the deployment of the solar rays and the deployment of the boom here, the boom of the wind sensor. Going to detail of the subsystem, we start with the electrical power subsystem because it's the main driver for the configuration. So we have decided to have a classical, reliable photovoltaic system with 4 extendable body-mounted panel. And the secondary battery, we have decided to use a lithium-ion battery. We have also decided to have a sizing strategy for this kind of subsystem because fixing the area and knowing the radiance during the day, we know also the available power for our system. So knowing the value required by each subsystem, each mode, we can try to fit the shape. Here we have science mode and telecom mode that are the most requirement that requires more power of each mode. So we can always satisfy the requirements in terms of more power with our available power. So here we have the power budget and the mass budget of the system. We have decided to use a PCDU as a PCDU, a direct energy transfer with a regulated bus, mainly because of the presence of the lithium-ion battery. Then we have the thermal control system that is driven by the low power available. So we want mainly to remove heat from the hot equipment during daylight, but we want also to minimize heat losses during night. In order to do this, we have decided to have a night thermal insulation, also a variable thermal conductive path. Going to detail of the configuration, we have this box, the electronic box connected to the radiator, as already said, with 4 paraffinic switches. This is allowed to dissipate during daylight the heat from the electronic box, but also to decouple the electronic box from the external environment during night. We have also the electrical meters unit here and also on the wind sensor in order to heat up the system, and also 5 TH. With this kind of configuration, we can see how we can respect all the temperature range for each element, both in the worst code case and the worst code case. Here we have a mass budget and a power budget. We have decided to don't use MLI because of dust and atmospheric issues. And we are focused on the study of the thermal conductive path because it's critical for a strong design of thermal control system. Then we have data. We have collected data and we have to manage data. So an OBDH system is needed. So this is the architecture of the OBDH. We have a primary bus, data bus, and a redundant one connected to the attitude and to the payload. Then we have a remote terminal unit in order to manage the data that we have. We have two processors working not redundancies. These are 6000 base 32-bit. Then we have the storage, so memory 16 gigabyte. Here the article of the telecom. So we made a study on the Martian atmosphere, so focusing on the losses and the attenuation, mainly related to the fog clouds, aerosol, and dust storms. In this graph, you can see how in polar and Ballis region the losses are almost equal depending on frequency. But in southern hemisphere during the storm, the losses increases a lot. We've also made an analysis on an equivalent noise temperature, considering an upward-looking antenna and downward-looking antenna. With an upward-looking antenna, we can see how the equivalent noise temperature is lower, so we have decided to use this kind of configuration. Going to detail of the link budget, we have constrained on the power, the amount of data, and the visibility windows depending on the orbital motion. So we have decided to have this signal over noise ratio, considering margin and considering also the wanted bit error rate. So considering losses and the equivalent noise temperature, we select this frequency mainly because of the losses and the low power available. So this is the results for what concern the linear transmitter. So two linear antenna because to have a true coverage between the orbiter and the gondola. This is the receiver, a parabolic antenna of 3 meter. So this is the results of the data rate from the link budget. You can see how this red line is the data that we have to transmit. This is the data that we actually can transmit depending on the distance between the orbiter and the gondola. So we see how in the first place we cannot transmit enough data, but then with the peaks we can manage also this situation. So we compensate initial phase. We can also see how in the storm we cannot transmit almost anything. So this is not a good solution. It's not a good situation for our telecom subsystem. So in tropical balloon and polar balloon, we can transmit enough data. During the storms, we can't. Then we made the Fintan model analysis in order to evaluate the loads, the response to the loss of the structure. So simulating our structure, we evaluated the load, so gas loads, heavy braking loads, and also the wind of the extended panels during the storms. We have seen how no yielding, no buckling, no deflection of the boom tip occurs during the storm. So I will leave the stage to the last part and will explain you the ground station of our mission.
Good morning, everyone. I'll be talking about the ground station, also known as the Moses. Starting with the configuration, we had two main drivers for the configuration that we selected. The first one was the ground station had to be small enough to fit inside the limited volume of the entry vehicle. And the second one being the solar panels which were used to power the instrument should have been big enough to last the entire lifetime. Based on that, what we decided on was the cylindrical disc configuration, which was 25 centimeters high and 87 centimeters in the diameter. It was divided into two sections. First, the top half contained the 4 deployable solar panels, which would be deployed whenever needed. The second half was again divided into two sections. One called the bomb box. As you can see, it contains all your batteries, PCDU, amplifier, and the electronic equipments, while the second half contained all your instruments and the sensors needed for the mission. As you can see in the demonstration, once the ground station touches the surface, first off, the solar panels are deployed. Secondly, we have a robotic arm which will be used to deploy the seismometer on the ground to avoid any sort of noise in the data. Then we have also considered using telescopic booms to deploy all the environment sensors so that there is no interference from the ground station to the readings. As you can see, we have a linear antenna also, and this displays your pressure sensor and the temperature sensor booms. Moving on to the electrical power subsystem, as you already saw, we had 4 deployable solar panels, which were accompanied by a secondary battery. This was mainly driven by 2 factors. First was the specific power, second was the reliability of the system. And the idea was here to meet the power demands during each mode and phase. This was computed using the peak power consumption, and as you can see from the graphs, the highest power needed was during the telecom phase, followed by the science phase. So what we did was to try and restrict all our high power activities at the time of availability of highest power, which was between 10 and 3 in the Martian hours. And the blue line here clearly states that the available power at that moment was way higher than what was needed, and we were able to satisfy all the requirements. Then to conclude with the EPS, I show you the mass and the power budget. And to add up, we used a PCDU with a direct energy transfer with a regulated bus. Then talking about the thermal control, here the main idea was same as that of the aerial segment, to keep the components in their temperature ranges by minimizing the heat loss while also radiating any extra additional heat that was generated. However, one important drawback, or let's say limitation for the ground station, was its contact with the Mars surface. And during the night, that would have acted as a source of sink and depleted the ground station of all the heat. To overcome that and all the other problems, what the strategy was applied was use of aerogel all over the surface for insulation, then adding up a radiator to the circumferential area of the warm box, which was controlled by 2 paraffin-based thermal switches. Then to heat up the system, we had 1 electrical heating unit and 5 radioisotopic heating unit. And to finally cover it all up, we wrapped it up in golden coating. Then multi-node analysis was done on that configuration, taking the worst case for both Halus Malaysia and Valles Marineris. And as you can see from the graph, the purple line indicates the operating range, and we were clearly able to meet all the requirements. Then to conclude the thermal control subsystem, I show you the mass and the power budget. And in this case, I'd like to add one of the proposed technology here was to use mini loop heat pipes to guarantee a uniform distribution of temperature, and it being as a lightweight alternative. Moving on to the onboard data handling. In this case, the main driving factor was the selection of the sensor suites that we had. And since we had mass limitations, we tried to find the sensors which had built-in application-specific integrated circuits. As a result, what we decided on to use a single electronics board that would contain a processor capable of delivering 25 megahertz. It was connected to the sensors using a 1553 data bus, and all the data was managed using our integrated remote terminal unit. Finally, we had a local data bus to connect the RTU with the processing units, and a 16 GB of onboard storage to store all the scientific data. Finally, to transmit all the data, we move on to the telecom subsystem. In this case, since we had no regulation on the bandwidth usage on the Mars environment, the main drivers came from the power available to the system, which was around 7 watts, and the losses which were specific to the Martian environment, as mentioned earlier. So taking that into consideration, we took a signal to noise ratio of 8.6 dB, and we came up with a frequency of 400 megahertz, which was transmitted using a 0.7 meter long linear antenna and received by a 3 meter wide parabolic antenna on the orbiter. As you can see from the graph, the top one represents your link budget, while the bottom one represents the amount of data transmitted. The green line in both cases represent the amount of data that we were able to transmit during the dust storm, which was not feasible to do. However, under normal circumstances, as you can see, the orbiter gets closer to the ground station. We had a peak in the data transmission over here, and we were clearly able to transmit all the data that was generated during the mission. Then to continue from here, I invite Marco Cherubino.
Good morning, everyone. I will guide you throughout the most critical part of the whole mission, probably. That is the entry vehicle entry, the descent of it, the partial deployments, and the balloon itself that is deployed and demonstrated. So we can divide this macro phase in 3 sub-phases. So the first one, the entry vehicle atmospheric entry. The second one, the deployment of the parachute, the supersonic parachute. And the third one, the subsonic probe inflation with the parachute, with the balloon inside. So this is a sketch for the whole phase. 1, 2, of course, are the entry vehicle. 3, 4, the supersonic parachute deployments. 5 and 6. The subsonic probe release, the violet one, very big, as we'll see. with inside the balloon inflation. So starting with the first one, we consider the entry in the atmosphere of the entry vehicle at an altitude on Mars of 110 kilometers. And one major constraint was to assure a velocity at 20 kilometers in altitude below 400 meters per second in order to assure correct deployment for the supersonic parachute. And actually, we have managed it quite well because from the simulations, in 281 seconds of exploitment of the drag of the entry vehicle, we arrive at 368 meters per second. We experienced a maximum acceleration during this phase of 3.1 Earth Gs, so 9.881, and that's it for the entry vehicle. Then, at the end of this phase, it's released the supersonic parachute, that is a 6.5 meter in diameter disc gap bend type. It's pretty big, but it has to do its job. In 40 seconds of operation, we arrived from the 20 kilometers altitude when it has been deployed to 13 kilometers in altitude, lowering the velocity down to 110 meters per second. Then we entered the most critical subphase of all, that is the inflation of a very huge subsonic drop, as I say, the violet one. Here the system is composed actually by, we can see three main subsystems: the balloon here in red, actually here is inflated, the subsonic drop, the violet, and a pre-parachute that is a cross-type parachute. In the drogue, in the envelope, you can see these are scoops in which ram air can be taken in order to have a proper displacement working with the pre-parachute. And there are two main jobs that has to fill the subsonic drogue. One, of course, to slow down our system. As you can see, being it's really huge, it can slow down to 22 meters per second. And second one, to prepare a protective environment for the inflation of the gas cell. So this phase lasts for 120 seconds when inflation must occur, so very, very strict time. And there is a maximum acceleration experience of 9 Gs actually when it's deployed the subsonic probe. Anymore. Okay, sorry for that. So we can see that inflation is completed, if you have seen before, at 9.5 about kilometers in altitude. At this point, we need to release the subsonic drogue in order to provide the steady state flight for the balloon. So what we have in mind, we first of all release the ropes here. They are nylon-made ropes with USA military standards, nylon-made. There is the rip-off of the stitches here, as you can see. And with the help of the ram air intaking from below and through the pre-parachute that is still deployed, we have the slip-off of the whole drogue. That is because we complete the inflation before reaching the steady-state density of 8,000 meters. That is the case for the tropical balloon. Actually, the polar one is even lower, so it's even better. The stitches rip off, the drogue slip away, and we have so the complete steady-state flight for the balloon. We need 15.5 kilos of helium that must be inflated in 120 seconds. So here is the mass flow rate, 130 about grams per second. And so where is Moses? Where is our ground station in everything here? Moses is attached to the back of the heat shield. So towards the end of the supersonic parachute phase, it is released, the heat shield, with a touch on the back Moses. Then Moses deploys its parachute. After deploying its parachute, that is a disc gap bend type model as the one for the supersonic one for the entry vehicle. There is the detachment on the entry vehicle and relative structures that are still attached, I remember, at Moses. And then before touching the ground, osmosis airbags are inflated in order to have a correct impact. These are main parameters for the parachute. As I say, these are this gap band type. And these are velocity profile for the descent, acceleration profile with a peak of 3.5, less than 3.5 Gs, Earth Gs also here. And this is the altitude. It's quite linear because steady state on the descent, as seen here in acceleration, is reached quite fast. And the overall descent lasts for 515 seconds when of course the impact. This is the brother of the rendering behind me, beautiful Moses. And now let's talk a bit about the entry vehicle, the inside of the entry vehicle with its subsystems. We have 12 helium tanks dedicated for the inflation of the balloons. These are radially and equally spaced displaced in the entry vehicle, as you can see. There is the propulsion subsystem pressurizing and feeding system here. So 2 tanks for the monomethyl hydrazine and 2 tanks for the nitrogen tetroxide, with 2 tanks of helium for the pressurizing system. There is Moses, our ground station. So as you can imagine, this is one of the tropical balloons because it has Moses inside. There is the gondola in its folded configuration with folded solar panels here and here. We have the 2 parachutes. The red one is the supersonic one, and the yellow is the subsonic one. And we have the balloon cell, as you can see, quite big. So what we have done to validate our shell of the entry vehicle, we performed a CFD analysis to validate also our models for the descent, and we used through a computational fluid dynamic analysis using CO2 flow. Actually, Mars atmosphere is 97% in CO2. We obtained a drag coefficient of 1.45 that in literature is quite accurate because they're usually between 1.4 and 1.5. We have a neat flux of up to 5 watts per centimeter square. You can see the Mach number and the maximum temperature reached for the fluids. That is, of course, as you can see here in front of the heat shield. Well, this is just sketch. It's quite hard to see, but the Mach number here is up to 781. Velocity contours with the shock flow, and here is the flow temperature as already states. So what we have done instead with respect to the structural analysis through a finite element model, we designed aluminum alloy shell, taking into account the gravitational acceleration and the pressure that has to be sustained during the descent. Due to the very thin atmosphere on Mars, we have a pressure during the descent, a peak pressure in the dynamic pressure of 3,500 pascals onto the heat shield, with an acceleration inside for the various masses of 17 Gs. So numbers were really small, but I say stresses here are very, very far from the aluminum yield stress value. We are about 9 megapascals of stress maximum stress onto our structure. And in order to have an even more conservative design, we just modeled to sustain all the loads the external shell without considering any internal reinforcements. So with internal reinforcement, it's even better the situation. Talking about instead about the attitude control system, we have as a requirement for the precision landing to have a no lift component or the aerodynamic force, and we provide this with a PID and pulse width pulse frequency modulation controlling our force secondary thrusters. And we have as a main goal a pointing error with respect to velocity error of the vertical axis of our entry vehicle, less than 1 degree. And we obtain a very, very nice value that is actually lower than 0.3. Here, disturbances has been modeled with a strong white noise, and so the system stiffness is proven. Here is a sketch for the torques for the moment about every principal axis of inertia of our entry vehicle. And then we talk about the propulsion subsystem that has to be performed, the orbiting kick and the attitude control, as already said. As you can see, Delta V has been tailorized by Amedeo mission analyst for every entry vehicle in order to save mass, because our main driver is always mass saving because of the huge components we have on our mission. So as you can see, there are 3, 1, 2, and 3 in red main engines radially disposed that are provided by Aerojet. They are in class of 110 Newton, paired with a secondary subsystem of 1 to 3 and 4 in purple here in the sketch from ES Astrum that's our 10 Newton class to attitude control. The overall system is a bipropellant system, of course you saw, monopropellant and nitrogen tetroxide. And here on your right-hand side, you can see a sketch for the direction of the flow of the secondary thrusters. So it's 48 degrees here, you can see inclined with respect to the vertical axis to provide torque, and here the spinning capabilities if needed. So this is the sketch for the pressure regulated system. It uses mainly latch valves to control single seat latch valves to control the secondary propulsion system, and double seat latch valves instead for the primary propulsion system. This is the mass budget here on top. As you can see, they're quite similar, but we have actually saved about 15 kilos more or less, tailoring every one of the entry vehicles. For what concerns electrical power needs, we have a peak of less than 300 watts that occurs during the detachment, and so with the primary and the secondary secondary systems acting of the propulsion system. So latch valves, double solenoid, and so on. And now I leave the word to Andrea that will talk about demos.
Thank you. When we dealt with the configuration of our orbiter, the main concern that we had is the position of the 3 entry vehicles that are quite massive, and therefore they will be deployed in a long time. And so we try to maintain the spacecraft as balanced as possible, because we made some simulation and the attitude control system would be too big in order to control the unbalanced configuration with another position of the entry vehicle. So we decided to align the entry vehicles with one axis of the spacecraft that will be the nadir pointing axis in order to enhance the gravity gradient stabilization of the attitude. We fixed the panels orthogonal to the nadir axis in order to allow the rotation around the nadir axis to maintain the solar panel as close as orthogonal as possible to the sun, without 2 hinges with 2 joint with 2 axis control. The nadir Mars antenna that its orientation is controlled by the attitude control system. And to fit inside the launcher, we need the foldable solar array and the retractable antennas. Moreover, for what concerns the structures, that was another main problem for the orbiter, we cannot attach anything to the heat shield of the entry vehicles. All this configuration has a major drawback of complicating the mission if one entry vehicle's deployment will fail. As I say, this is our orbiter with the 3 entry vehicles aligned, the 2 solar panels. This is the nadir pointing antenna that is fixed, just deployed, and then the attitude control system pointed to Mars, and the measures of the whole spacecraft. This is the one main section. You can see the main body of the orbiter is devoted to maintain and have the propellant tanks and pressurizing tanks mainly, and all the minor instrumentation, and the external reticular structure to feed the 3 entry vehicles. When we deploy the first entry vehicles, obviously we will deploy also the reticular structure that protect the second entry vehicle. In order to perform this maneuver safely, the main engines kick the orbiter on a safer orbit far from the reticular structure that has been released. And this mitigate the risk of the mission, because if, for example, the entry deployment system of the first entry vehicle fail, we are anyway able to detach all the structure and release always and anyway the second entry vehicle. For what concerns the internal instrumentation, we have mainly as I said, the Mars antenna that is just deployed, the Earth antenna that is two-axis control in order to point the Earth without affecting attitude requirements. We have the radiators and the star sensor that are aligned obviously along the solar panel axis in order to minimize the pointing to the sun of these components. One of the 6 pair of reaction control thruster, this one is the one that makes torque around the nadir axis, and all the internal instrumentation, transmitter, OBDH, PCDU are or inside the thin substrate of aluminum that is not well seen in the picture, that is folded with MLI and so protect thermally the instrumentation, or if they can be lower this part, they will be folded with MLI. This is the operation around Mars with the Mars pointing antenna, the two-axis control left antenna, and those are the only instrumentation that carry the orbiter. The orbiter is mainly a deployer of entry vehicles, but we fit this phase to install 2 cameras and 1 spectrometer to perform anyway analysis on Mars. This is a representation of the deployment of the antenna. Actually, this is turn 180 degree when it hit the launcher with the feed toward the entry vehicle and not starting in this video. But this is the final configuration that we obtain when everything is deployed. The attitude dynamics control system drive mainly the configuration of this orbiter, as I just said. We have a nadir pointing mission basically, and the Earth antenna do not impose any requirements on the attitude dynamics control system. We only require the nadir pointing mission with nadir pointing error less than 1 degree and a rotation around the nadir axis to maintain the solar panel orthogonal to sun within 5 degrees. We need maneuverability for the deployment because we have to reorient all the main engines to perform the safe maneuver. We need to be stiff during the air braking, the firing modes, mainly during the air braking with the huge big panel that we have. We cannot vary our attitude. And we envisage an emergency maneuver if one entry vehicle will fail its deployment. We can be able to have an emergency slew rate of 1 degree per second with all the 4 reaction wheels that we have and the 12 reaction control thrusters. Indeed, these are the architecture of the attitude dynamics control system with 2 star sensors that provide the main attitude determination, 8 sun sensors that provide almost full coverage of the environment, and they will be used in safe mode and to acquire the initial attitude. The big 4 reaction wheel that provide the maximum torque of 0.4 Newton per meter, and the 6 pairs of reaction control thruster. We try to maintain, however, the dry mass as low as possible, also the nominal power as low as possible, and we have only a peak power that is quite high for the emergency maneuver just presented. These are one simulation when the orbiter acquired the altitude starting from an initial ground condition. It is able to acquire the altitude well below the imposed limit because we have 0.1 degree of error in nadir pointing, less than 1 degree of error in sun pointing, and this maneuver is made in 750 seconds. The reaction wheels have to perform this work in order to perform the previous maneuver. The second main concern about the orbiter is the structural part, because we have to provide an external support for the three entry vehicles without attaching anything to the heat shield. The design case is the inertial loads that are present during the launch, obviously, but with these huge masses attached to a so thin structure, we have a lot of problem to meet frequency requirement of the launcher. But we perform the analysis, we satisfy and we perform the static and bucking dimensioning, and then the modal analysis to avoid resonance with the launcher vibrations. So those are the constraints, attached to the back shell, minimum frequency, and we conclude with aluminum strut structure with aluminum panels reinforced anyway with bar. Those are the inputs, so the flight envelope of the launcher, the Delta 4 EV. We made a finite element method analysis to perform this computation, and we also checked that the aero braking loads are withstand by the solar panels with these solar panel substrate. This is not a problem mainly for the hinge, because we obtain this flexural momentum at the root of the solar panels. This is the result. These are the result of the simulation. The maximum displacement is well below the requirements from the launcher, so below 5 millimeters. The maximum stress is also acceptable, and mainly we are able to provide higher frequency with respect to those required by the Delta 4 EV. According to the mission analysis, we have the Delta V to be provided by our main propulsion system, and is mainly after the launcher injection in Mars transfer orbit. It is only in charge of our main propulsion unit with 1.2 thousand of meters per second of Delta V provide. Obviously the main engines are posed very close to the center of mass to avoid attitude disturbance in case of failure. The 6 pair of secondary thruster to perform all the control maneuvers, and the class of 890 newtons MMH NTO primary propulsion system, and MMH NTO 22 Newton thruster for the secondary propulsion system. This is the sketch of the propulsion system with the two main engines. It's pressure regulated and basically contains all the stuff that we need to make work the system. With the mass budget that is obviously the most relevant for the whole mission, because 1.7 ton of mass for this system, obviously for the propellant, and peak power consumption of 140 watts to make all the valves and pressure regulation system working. For what concerns the thermal control system, we have a narrow temperature range to satisfy, and mainly we have to face different configuration after the entry vehicles are deployed. For this reason, we implement the thermal control system that has to be stiff to external variation for the different phases of the mission, obviously, and all is regulated on the global insulation to localized dissipation. And this is the solution with the entry vehicles that are actually covered by MLI to protect them during the transfer. We have the radiators that are installed with louvers to control and better control and tune the deep space dissipation. And however, we need 365 watts of electrical heater units to maintain mainly the payload of the entry vehicles warm enough. Those are the situations that we have to face. The disappointing attitude during the interplanetary transfer makes our most cold case, because we have only this phase exposed to sun and all the rest of the spacecraft exposed to this phase. And then on Mars we have normal configuration for what concerns the thermal income. So as I say, the cold case is during transfer for some pointing altitude, while the hot case is when Mars is at perihelion and our orbit is without eclipses because of the right ascension anomaly. But anyway, we are within the ranges of the instrument, because obviously this is the transfer with the coldest body temperature, and the panels have the highest body temperature because they are continuously pointed to the sun. While around Mars we have the situation with 3, 2, 1 and 0 entry vehicles. Obviously the first entry vehicle we are always well below the required limits. In this situation the entry vehicles protect somehow the body of the orbiter from dissipation. We lose one entry vehicle. Then when we lose another entry vehicle and another entry vehicle, we have the body that is still colder because of the more are exposed to the deep space, and so the body needs more power from the heaters. This is the design and the thermal control system. We need quite amount of MLI to protect all the body and all the entry vehicles with the louvers, and the power needed by the heaters, mainly for the reason that I explained before, when all the entry vehicles are deployed. We make a very robust thermal control design because we take into account the possible degradation of the MLI during the aerobraking maneuver. So we consider the MLI with very low performances, because we consider the possible degradation of these materials during the aerobraking. And as I said, also the entry vehicle needs MLI insulation to protect their payload. Now Silvia will present the last system of the orbiter.
So starting from the OBDH, that is the core of the software part and data handling of our system, the requirements of this subsystem are the high on autonomy, the survivability to high radiation doses of the components, and the high payload data rate that it has to manage. And these high level requirements has to be satisfied, considering constraints given by the TRL of the available components, the limitation that we have on the overall mass of the system and of the power, and the compatibility of buses that we want with high speed with the components we selected. And the solution is found considering using latest available units and components that should be radiation tolerant. Another requirement, as you can see here, is the tracking and positioning of AMOS, that is the aerial platforms. And this was solved using algorithms for tracking these objects. Looking to the architecture of the OBDH, it is done with a distributed bus to grant high reconfigurability and redundancy. As we can see here, it is made with 2 data management units to control as a control. The first one dedicated to attitude control and housekeeping data, and the second one dedicated to payload data. And each one is made by 2 processors in order to have redundancy. Inside the DMU2, we have the tracking algorithm implemented, while then we have an RTU connected to the DMU2 in order to have connection between the sensors and the platform. And then we have the 2 memories to store all the data. And here are some components that have been selected and the tracking software we selected to use. All the data collected on the orbiter comes not only from orbiter itself, but also from the other segments, since the orbiter acts as a relay between the segments and Earth. So with the constraint of this quite huge amount of data to be transmitted, and the constraints on the power supplied to the telecom system, and in order to grant the signal to noise ratio desired, we perform a link budget, selecting as the downlink frequency the 32 GHz, and with a 3-meter diameter parabolic antenna and the deep space network as a receiver, what we get is that this is the total amount of data we can transmit in blue, and in red, the total amount of data that we should have to transmit, obtained, taking into account again a constraint that comes from mission analysis, that is the number of visibility windows and the duration of each one. But as we can see, we are able to transmit all the data we have within the visibility windows we have. And at the end, I want to present you the EPS, since all the subsystems we have seen until now requires power. And as a drivers for this, we use the specific power and the reliability. See, the specific power in order to not increase the mass too much, and the reliability in order to not increase the risks, since the mission is quite risky by itself. And the design relies on 2 solar arrays and a secondary battery. Since the requirement of the propulsion system, the power subsystem is to support the power demand for both average and peak loads for each mode and each phase. We performed a power budget, and as we can see here, the most demanding phase is the telecom one, and this is not only the most demanding one, but also a recurrent phase, since it can take place once per orbit. And so the sizing strategy was to consider the power in daylight the one required for telecom mode. This is the budget we did with a solar array area of 23 meters square, and the selection of the batteries that are secondary batteries lithium ion. And since they are very sensitive to charge and discharge, we selected as a PCDU with a regulated bus. And at the end, we did an additional analysis in COMSOL model to simulate the arrow braking, since the drag increases the heating of surfaces. And the condition we selected is with the rear face of the panels oriented in the direction of motion during the arrow braking. And as we can see here, this is a simulation. Here is the area where cells are placed, and this is the substrate. And as we can see, the temperature is lower at where cells are placed, and it never goes, and it's always under 150 degrees. For this reason, we decided to put all the wirings and connectors on the front face of the solar panel, and that each material and process for the array must be investigated for its ability to survive at these temperatures for multiple exposures. Now, there is a massive power budget, since both has been for the overall project. Some drivers we have to take into account, since this is for AMOS, one for the tropical and for the polar balloon both. And as you can see, they have quite a huge mass. And while moving to the entry vehicle, the mass increases a lot, and that's why it has been a driver for the overall mission. And then here is the overall mass budget for demos with both the dry and wet orbit, for wet and dry mass. And here a total considering the margin and the adapter. And looking at the power budget we have done for each subsystem again, considering also a dust storm mode for both the MOSIS and DAMOS, as you can see here, in which we have just to survive, since we are not able to do anything else. And here is the overall budget for demos. And now, to draw some conclusions, as we can see here, these are the most critical aspects of the project we have talked about until now. And as we can see, the most critical aspect is the inflation of the in-flight inflation of the balloons, since it has a low TRL, and this means that we have to reduce this risk index, and this should be done with the test campaign in a similar environment to the one we could find on Mars. And the other are other risks we can have in our mission, but with a lower index. And considering all these critical points, not only about the low TRL or the inflation technology, but also to the lifetime of aerial platforms and to the low number of ground stations, since we have a requirement of 4, but we are able just to have 2. We can say, by the way, that mission is feasible because all required scientific data are collected. So that's the end of our presentation. Thank you for your attention. And if you have some questions.
Just one short question because of the So I suggest to have a very short question now for them, and then at the end of the whole presentation, if still something wants to be asked to the team, can be done. Otherwise, we goes on.
We can ask that if they have some beautiful video of the beautiful t-shirt.
For you.
Extra large.
I mean, if it's
How did you find the wrong component?
sorry, there is at least one technical question, otherwise we jump to the other.
For the aerobraking phase, which driver would you consider design phase?
We try to maximize the area of the spacecraft, but taking into account that to lower the risk with thought of the altitude being with the entry vehicles aligned with the velocity vector. So, like this, if the velocity vector is in this direction, and this is the altitude for the aerobraking, with the panels reversed, and the driver was trying to have the loads in order not to have a too strange configuration and to minimize the time somehow.
From the point of view of the loads to be there, we consider heat flux.
Yeah, we consider the X flux on the back of the panels and the load on the panels because they are
Dynamic pressure.
Yeah, the dynamic pressure on the panels and so the torque that is on the engine itself. They were very fast.
Thanks again to the team. I invite the Galaxy Ranger to come. So the Galaxy Ranger wants to come or wants not to give the presentation? Dovreste accelerare un attimo.
Guarda quale è delle vostre, ho capito, lo aspettiamo, però intanto prepariamo. Qual è la giusta?
Questa lo schiamo principale.
Questa?
Sì, l'altra per
Ok, l'altra però perché non so come metterla, l'altra dovrebbe essere da lì. Ok, qui dovreste stare a posto. Questo deve essere da qui. Questa, giusto? Ma non
So we can start with the second study that is completely different as an objective, and we are focusing on a telescope to work in the X-band and to be located in L2. So please, the team can start.
Good morning, I'm Simone Cocciago. I'm the team leader for this last presentation, and I'm a member of the Galaxy Ranger team. I will explain in a while the choice of this name. Galaxy Ranger is the anagram of two words, X-ray and Lagrange. But why X-ray and Lagrange? Because the mission objective is to map the X-ray universe in order to obtain important improvements with respect to previous missions such as Chandra and Newton XML. Lagrange because the requirement is to put the spacecraft in the Sun-Earth Lagrangian point L2. Other requirements are related to the operative life, which must be at least of 6 years, are related to the launch after 2025, and then are related to the possibility to have a full coverage of the celestial sphere. The payload is represented by optics and sensors. We need to guarantee a 12-meter focal distance for each operative phase. Then the sensors works alternately, and therefore a translation mechanism is required. Also notice that very stringent constraint on the resolution because it's very high. But why L2? The Sun-Earth Lagrangian point L2 is important because we can have an uninterrupted observation of the deep space, in particular of half of the celestial sphere, without having the Sun in view. This is important because the Sun is a strong source of X-rays, and therefore it can alter the measurement for science. Then, a few words on the environment in L2. The main issues are related to plasma, radiation, and meteoroids. Regarding the thermal environment, it's stable because the constant solar irradiance is constant. Some effects of these issues are related to the surface charging and degradation, to the total ionizing dose for the components which have the energy due to particles, and then meteoroids environment can be taken into account as a probability of impact. From a pool of different configuration, we decide to have a single launch and a monolithic rigid structure. The phases are the traditional one, I mean pre-launch, launch, commissioning, the transfer to reach L2, the operative life, and then the decommissioning. Notice that we have a safe mode in order to solve the problem we encounter, and then considering the operative life phase, it's possible to notice that the 80% of the time can be dedicated to observation, so can be dedicated to science. Now, I'll leave the word to Arianna, and we can start with configuration.
Good morning. So, this is the Galaxy Ranger. Here you can see some dimensions. The length, of course, has to be higher than 12 meters, but actually we only added a small room here for the sensors, while the diameter goes from almost 4 meters to 2 meters because the main bus is around the tube of the telescope. Here you can see how it will be inside the fairing of the Ariane 5. Which is the Ariane 5 because it has the more stringent dimensions. And you can see that the panels will be folded in 3 pieces and then folded and fixed along the main body. You can also see that part of the telescope goes inside the adapter of the ATV, that is the one we chose. Now let's have a look at what is inside. Inside the main bus, you can see there is a plate with tanks for both pressurizing gas and fuel, and on the other side all the electronic devices. Then there is a ring at which are attached 4 reaction wheels. The 5th one is inside the tip. Around the tip there are the thrusters for the transfer. Around and not on it, not to cover the visibility of the 2 antennas. We also have a 3rd antenna that is phase array. As this will be better explained later by our DCS expert, we managed to have one side always in light, while the other is always in shadow. This is why the antenna is in the sun side, while the radiators that you can see here tip, as I was saying, there are the two tensors with the translating motion, and around this ring that is aligned with the center of mass, there are the 24 thrusters that we use for both station keeping and the saturation of the wheels. So you can see another one. Now I leave the word to Paolo.
Good morning, I'm Paolo Musini. I'm going to talk about mission analysis. First of all, for the nominal trajectory, the first approach was based on the circular restricted free-body problem. The drivers for the orbit definition came from for EPS and thermal, because we want to be always in light, for the power supply, of course, and also to reduce the thermal gradient of the telescope, which is an important point for us. Also, another restriction came from telecommunications, because the Earth between the Sun and the angle between the Sun and the Earth should be high enough in order not to have the Sun and the Earth aligned. Because when we point to the Earth to communicate, maybe if the Sun is right behind, we could have problems with the noise. So then we decided to use a halo orbit around L2. In order to get to L2, we want to exploit the fact that we have stable manifolds, and there are stable manifolds. So the delta V needed for insertion in that manifold will be also a driver for the final selection. Here you can see the final selection. We have a halo orbit with an out-of-plane amplitude of 345,000 kilometers, a period of 180 days. And the delta V for the insertion in the halo, which is around this point, is 4.5 meters per second. For the decommissioning strategy, we want to exploit the existence of unstable manifolds. So having a small delta V of 4.5 meters per second, like for insertion, you can see here, we will be inserted into an unstable manifold and go away from the operational orbit in an orbit around the Sun. This is the trajectory close to the Earth. We have computed that the optimal insertion point is at 250 kilometers of altitude. So we have to arrive to this point, insertion point, with the velocity conditions we would have in a reference orbit, a circular reference orbit in yellow. And at this altitude, of course, with an inclination of 8 degrees with respect to the equator, in order to have a delta V, an acceptable delta V for the insertion maneuver, which is finally 3.4 kilometers per second. The total transfer time from the insertion point to the insertion point in the halo is 125 days. So this is our orbit. It gives us some constraints in the launcher because we want to use the upper stage of the launcher to perform this delta V of 3.5 kilometers per second, and also in the launch date. But first, I'm going to show you a video of the orbit, if I can do it. So as you can see, this is our spacecraft. This is the transfer orbit. This is the final halo orbit, and this is the shadow of the Earth. So you can see it's well avoided during the whole trajectory. And so this is the orbit of the Moon. Now I'm going to talk about the constraints I was talking about before. The launcher is a critical point for our mission, not only because we want to do the insertion maneuver with the upper stage, but also because of the minimum bending frequency and the fairing volume. As you could see before, and you can see here, we have a 12 by 3 meters telescope, so we must be sure that it fits in our launcher. So taking this into account, and also the political and economical reasons, we have two main choices: the Ariane 5 and the Delta 4 Heavy. This is a table with the fairing length, fairing diameter, and the minimum frequency. As you can see, these are higher than ours, so no problem with that. And for the minimum frequency, you will see in the structure subsystem that we are also above this frequency. And here we have computed the upper stage capability starting from a LEO orbit of the upper stage. So we have the delta V here and the mass of the spacecraft here. To have a delta V of 3.4 kilometers per second, the mass to be launched with Ariane 5 is around 6 tons, and the mass to be launched with Delta 4 is around 10. So you will see later that we are under this value, and as we prefer to be launched with a European, we prefer to use an European launcher, we selected the Ariane 5, but we have Delta 4 as a backup just in case. For the launch date, the constraint to to choose the launch date comes from the year, of course, can be performed before 2025. The relative inclination between the equator and the reference orbit I was talking about before. The minimum interaction with the moon. So as you can see, here's the first days of the transfer, and the moon is here. So during this trajectory, the moon will be moved during around these points. So it's far away from our trajectory. And of course, the visibility of the ground station during the first stages of the transfer, because we want to communicate. So with that, we have this table with the launch, which should be performed in October 18th, 2025. We have 3 backup dates, one month later, another and 2 more, one in 2026, another one in 2027, just in case there are some delays during the production. We have also computed that the risk to stay during this period of time in the launch base because of the gassing of the material is not high because the material selection we did for it. So anyway, if this is the optimal date in our windows, it's not that we can only launch in that day. We have we can move, but these are the better days for each window. Finally, I'm going to talk about the perturbations and the maneuver we do to compensate them. First, transfer correction maneuvers. We have to use them to correct the velocity errors during the insertion maneuver from the upper stage of the launcher, and also to compensate the effects of the perturbations. We considered the solar pressure using the cannonball model and the moon gravitational effects taken into account the ephemeridess. So as you can see here, the green trajectory is the one we will follow without transfer correction maneuvers. And as you can see, we are not in L2, which is the point. So with the transfer correction maneuvers that takes place in these 3 points, we arrive to L2. The transfer correction maneuvers should be done the second day from the insertion point, 17th and 78. And the delta V is 43 for the first one, which is the highest one, and a total amount of 67. These values are 20% matching because we didn't consider the eccentricity of the orbit in this calculation. We did consider the eccentricity for the final trajectory, station keeping strategy. So apart from the solar pressure, the gravitational effects, we have the elliptical problem. So you can see here a table with all the station keeping maneuvers we have to perform during a year in order to be around L2. The highest one is 2.7 meters per second, and the total amount is 18.3 meters per second for a year. Here you can see that finally the delta V budget with all the delta V for every maneuver, including the manifold insertion performed by the upper stage. So we have computed that for the 6 years, the total amount of delta V is 3.6 kilometers per second, and the total amount to be performed by our propulsion system is around 2,000 meters per second because of this is done by the upper stage. And then I will give the word to attitude and control.
The attitude determination and control subsystem is quite vital for a mission like ours because we have very stringent requirements coming directly from the payload. We need to be able to look at any point of the semisphere that doesn't contain the sun in that moment. And we need to do that in less than 4 hours. So to do any rotation in less than 4 hours. This led us to choose the reaction wheels as actuators because they can store angular momentum without using propellants. And we have to choose them with quite high torque. We need 5 of them. We will have 1 per axis and 2 for redundancy. We then have also high requirements regarding the pointing accuracy. We need to be below 1 arc minute for the absolute pointing error, that is the difference between the actual position and the intended one. While we need a very high accuracy on the absolute measurement angle that has to be less than the resolution of the telescope. And we need a relative drift over the acquisition time that has to be less than half of the resolution of the telescope, not to have 2 pixels continue one to another. And so we, of course, need star trackers as sensors. We have 3 of them. 2 are just to correct the high, for us, error they have on their roll axis. And the 3rd one is for redundancy. Then we have requirements coming from other subsystems. And the telescope has to rotate in such a way that solar panels remain as much as possible perpendicular to the sun. And of course, radiators should never be exposed to the sun. So in order to do that, we need to know the position of the sun. That can be easily calculated once the attitude is known from the sensors and the position from the telemetry. Just to have a reference in mind, we call z-axis the focal axis of the telescope, x-axis the axis going through the panels on which the panel can rotate. And this is how we managed to solve the problem to do the rotations. This is the telescope. And saying that the audience is the sun in this moment, if we need to rotate this way, it's not a problem, we just rotate the panels. But if we need to rotate that way and point this way, the panels can't be perpendicular to the sun. So we give away 1 degree of freedom and we control the rotation just on x and y axis. And the third rotation on z axis is guided by the other two. So we can rotate this way, then rotate on the z axis, and the sun has the solar panels perpendicular again. So what you are going to say to see in this slide is that these are some rotations of some angles, and you see that they take 1.4, 1.5 hours. The rotation is considered stopped when the oscillations have dumped under the values I was saying before. And we have quite a big gap here from those to those. That is due to the fact that those rotations require the telescope to cross the ecliptical plane. So in order to cross the ecliptical plane, if you want to see always the same side of the telescope, once you cross it, you need to flip it over in order to see the same side. So a model in Simulink was implemented, and the output of the model was passed to a virtual reality work on which we loaded the models, the CAD models coming from the configuration. And this is the rotation from the point of view of the sun. So you see that you always see the panels perpendicular to you, and you always see the same side of the telescope. You can never see the radiators that are on the other side, and you can never see the star trackers that of course can't look at the sun. And we have the same rotation with other points of view. No. The white stripe is the ecliptical plane. So this is a rotation that needs to cross the ecliptic. And the sun is coming from below in this view. And just one last video, that is this one, in which you see the rotation from the point of view of the panel. So this view is rotating with the panel, and you see the sun always in the same point. It's not moving, so it means that the solar panel is receiving radiation always in the same direction. And so in the model, some perturbations were implemented as well, such as the gravity gradient and the solar radiation torque. The magnetic torque was not considered because L2 is too far from the Earth for having interactions with our magnetic field. And the solar radiation torque is much higher than the gravity gradient one. We're talking about 7 order of magnitude. So it's actually the one that is driving the saturation of the reaction wheels, as it is the constant torque. And because of the rotations I was telling before, and because of having the solar panels always perpendicular to the sun, and so the x-axis always perpendicular to the sun radiation, the solar torque is absorbed always by the reaction wheels that are on the x-axis. So the redundancy is made, we have 2 reaction wheels just for the x-axis, so that we can use them both to store more angular momentum. And we, in the same time, we have redundancy. So if one breaks, we can still control everything with just one reaction wheel. And this is the time we can stay at a given angle with the sun before we need to desaturate the wheel. So the saturations happen with external thrusters that are the same we use for station keeping. And we apply quite a high, because they are the same, we apply quite a high torque. We are talking about 40 Newton meters. And the engines of direction wheels give millinewton meters. So it means that we have just 4 shots, very short shots of the engines in 300 seconds. And we can desaturate continuously. We have 2 of them, so these 4 shots have to desaturate them both in the same time. But during the desaturation, the absolute pointing error, that is the difference from the position and the intended one, is going to change a bit. And it's going to be over the requirements for the observation. So we need to decouple the desaturation mode and the observation mode. And we also see that we take quite a while before we can dump down this oscillation. So we have 300 seconds for desaturation and much more for bringing the telescope ready to fire again. Just to calculate a number, we gave some points equally distributed on the semi-sphere that doesn't contain the sun for the observation on the 6 years, and calculated that the mean angle of, between the z-axis of the telescope and the sun will be this one. So, given this statistical approach, we will have 740 desaturations in the whole mission, and this is the propellant required for each one. So, just multiplying them, we obtain almost 30 kilograms of propellant just for the altitude and the acceleration of the wheels. So, I give the word to Roman.
Good morning, my name is Roman, so I will be presenting the propulsion subsystem for our mission. For propulsion subsystem, the main requirements come from the mission analysis and ADCS, the delta V's and the desaturation of the wheel. The top table shows the various delta V's and desaturation that we need to do for our mission. From literature, we have found that the spacecraft that includes optics, like telescope, the conventional bipropellants and solid propellants are not preferred. The best solution is to use either a monopropellant hydrazine or electrical propulsion. So we did a preliminary analysis on both hydrazine and electrical propulsion, keeping drivers like mass, power, and complexity. And finally, we choose hydrazine as a monopropellant for propulsion. With keeping the specific impulse, minimum specific impulse of 224, we calculated the delta V budget that comes around 347. From here you can see the schematics that we're going to follow. We're going to have the 4 tanks for helium, total volume of 114, and 4 tanks of propellant hydrazine, each total volume of 351. So for the main transfer, we're going to use 2 thrusters, and to keep the full redundancy, we add 2 more, so in total 4. For desaturation and station keeping, since we're going to use same thrusters, and for the spacecraft having optics, it's better to keep the thrusters away from the optics. So the best configuration comes around 12 thrusters, and to have full redundancy, we will have 24 in total. So in the next slide, you see the placement of the main thrusters and the secondary thrusters used for station keeping and desaturation. For station keeping, the arrows that you see, one is going down and one is going up. It shows how we're going to apply the torque. But when we are using for station keeping, it's simple, we're going to use in the same direction. On the other slide, you can see the thrusters we are using. And this is the final mass budget that includes the pressure tanks, the valves, everything. And total with uncertainty, we come around 504. And the power budget for transfer and desaturation is shown. And I give Julio to further continue the presentation.
Good morning, everybody. I'm Julio Triberti, and I will introduce you to the telecommunication subsystem of Galaxy range. So the goal of our mission are, for sure, the setup an high data rate connection from L2 to deliver the scientific data, and an extended TT&C link to monitor our spacecraft. These two tasks are a little bit more difficult than this because we have also a highly variable attitude that makes this task stronger. So the identification of the requirements. Since in the CDS we knew that our telescope has a particular attitude, the constraints on the field of view of our antennas are hemispherical for what concerns the TT&C, and for what concerns the high data rate connection, we have to have a field of view that stays in a quadrant. So from the original 10 gigabits per day data rate, due to the encoding scheme that we selected, we have to double the data rate to downlink. This is a fair price to pay in order to maintain a good reliability on the bear. So now, by assuming 5 megabits per second, these 200 gigabits per day are translated into 11 hours and 6 minutes of compact time needed to download the data. As a nice to have, we would like to deliver the amount of data within the 24 hours in order to make it available for the scientists. So the first step is the communication architecture. Since no particular drivers were given for the architecture, we took the simplicity as driver. And for what concerns the ground station selection, we have two different families of drivers. So the first one in the X-band, which is the high data rate connection, we would like to remain European, of course, due to political economical reasons. We would like to have a big diameter in order to have a good influence on the overall link budget, and the visibility, which as said before has to be more than 11 hours per day. For what concerns the S-band, the drivers are, of course, again, to remain European, and then an extended visibility with respect to the previous band. So we have 4 ground stations, 3 in the X and 3 in the S-band, with 2 of them, Malarg and New Norcia, working in both the frequencies. So as you can see, between the drivers, there is the visibility, which is really peculiar, and I'm going to introduce you in the next slide. So the visibility is important, first of all, for the sizing of the batteries, because since we are in L2, we have no eclipses. So the batteries are sized with respect to the standby mode. We would like to maintain the spacecraft alive until the first communication occurs. So this was taken to size the batteries. While for the X-band, the maximum dark time that we have in L2 will size the memory. So the problem was faced by taking the orbits from the mission analysis, by considering the position of the ground stations, by considering 10 degrees minimum elevation angle beneath which no communication occurs, and by considering 15 minutes for initializing and ending the connection. So these are the outputs of this analysis, and as we can see, we are, for the scientific data, well above our request, and also for the TT&C we have an extended visibility. In this graph here, you can see the usage of each ground station on the overall ground segment. So there is a pretty equal distribution of the job between the ground stations. At the beginning, at the very first moment of our mission, we have to exploit the following ground stations, so Kourou, Natal, Ascension, to guarantee the contact for the first 20 hours in such a way to have the maximum dark time in the S-band, 3 hours and something. So the antenna selections, first we talk about the TT&C. The driver to choose the antennas was a wide coverage. So as you can see here, this is the radiation pattern of a patch antenna, which is this one, and this is the radiation pattern of the conical antenna. So by putting together these two radiation patterns, the result is a wide coverage antenna which has plus and minus 120 degrees. This is of course compliant with the requests that were hemispherical, and we have a 30% margin. So we can skip to the high gain antenna. For what concerns the high gain antenna, we would like to deal with a really variable attitude. This is why we prefer the phased array antenna instead of a steerable dish. In fact, if the mechanism would have failed, we wouldn't have been able to transmit in the overall hemisphere, but just in some restricted regions. So here you can see the antenna, and from this table, you can see that the link is really reliable, and what is important also, that the real time is guaranteed for the delivering of the data. Ending, there are the effects of the TLC, of the telecommunication subsystem on the other subsystems. So to the mission analysis was asked to keep the sun at almost 2 or 3 degrees away from the Earth. The OBDH, the sizing of the memory was given to the visibility. The same is for the sizing of the batteries, and the ACDS had to make one side of the telescope always looking to the Earth. So in the mass power and dimensions budget, we can see that we came out with a pretty low dimension value in terms of mass, while where the telecommunication subsystem affects the most is in the power, which is 400 watts. I thank you, and I leave the stage to Ismail.
Good morning. I'm in charge of the overall data handling system of the Galaxy Ranger mission. So first, let's focus in the drivers for this subsystem, coming mainly from the telecommunication subsystem for the autonomy. We have to take into account the ground station visibility and the high delay in the connection due to the distance to orbit. We have a download data rate of around 5 megabits per second for the high gain antennas and 2 kilobits per second for the low gain ones. We have the environment with a high radiation dose. And we need, due to our long and intense operation, we have to be very reliable. So the system should stay simple and deterministic. And of course, from the payload, the electronic payloads, that I will know into the details of the functioning of them, but we consider them as black boxes with an output whose maximum data rate is around 900 kilobits per second. The instrument control unit and other electronics take care of the compression of the raw data. So this makes no necessary of the usage of a payload dedicated computer. Here we have the architecture of the OBDH. We can see a centralized system with a central processing unit. We can see in this part the payload where the detectors are connected to a space-wide router. Also additional electronic as the alignment monitoring system that is very important to determine precisely the position of the detectors in the focal plane, and all is connected through the space-wide connection. For the high reliability system as the attitude control system, the electronic mechanisms and the power distribution unit, we use a 1553 bus, which is deterministic and has been proven for more than 30 years. With respect to the housekeeping and attitude data collection, we have considered the 4 main kind of discrete signals that are in the ECSS standards. The analog signal monitor, which is coded with 12 bits, the temperature signal monitor with around 16 due to the high accuracy we need in the temperature measurements, B-level discrete signals, and B-level switch monitors. We have also a lot of different digital connections that I will not go through them. And in total, we have around more than 2,000 channels of collection, keeping in almost everything a full redundancy and a data rate generated of around 17 kilobits per second. This data rate is really high, but we need it to control and monitor the spacecraft. We transfer it through the high gain antennas, but we need omnidirectional communication, so we create an essential telemetry channel reducing the acquisition of the data to around 30 seconds to 1 minute, and we have a total of 700 bits per second. So the power consumption of the antennas will be lower. Then in the processing app software, we have performed a bottom-up estimation. We consider the applications that we most suit our needs, and we have come with a throughput and software memory considering a 400% margin as the GPA recommends in the preliminary design review. We have around 1 million instructions per second and around 12 megabits of memory, in which is already included the operating system or executive that we selected the R10s because the recommendation of the European providers for the processors. Then we have the memory sizing. In these plots below, we can see the envelope of the maximum load of the memory, both for telemetry in green and for scientific data in blue, considering the transfer orbit and the 6-year halo orbit. And even if here is reported only 1 year because it repeats cyclically. We have considered the visibility with a precision of minutes. So there is the actual and real envelope, and the memory required would amount to a platform memory total of around 18 megabytes and a payload memory of around 20 gigabits. We have considered the worst case of generation of data of around 900 kilobits per second for 24 hours. That actually is not the most demanding case because we will share at the most for 80% of the time. And finally, we have performed a budget estimation considering that the electronics and the boards are actually built spacecraft dedicated. We have considered some component that has already flown in other missions and that already perform what we need. So we come with around 35 kilograms of mass for the OBD8 and around 77 watts of power. And I leave the word to Simone.
Who's in charge of the thermal control subsystem. The main task is, of course, to keep the components in their temperature ranges. But then, due to the peculiarity of our mission, we need also to maintain precise geometry and alignment between the telescope between the sensor and the optics. So the drivers of the design was the minimization of temperature gradient for the structure. And therefore, the design philosophy is based on the insulation of the whole structure from the external sources and the internal heat sources. We can notice here there is the sensor housing. Here we have the optics, and all the components are in the main bus. So the idea is to avoid thermal gradients due to the heat source, due to the heat generation. So considering the insulation from the environment, we decided to use an MLI insulation. This is because we have a very high area irradiated, and without MLI insulation, the heat flux is too high for the structure. As you can see, the outer cover chosen is the black cotton. Why black cotton? Because of the stability of thermo-optical properties, and this is necessary because we have a constant absorptivity during the whole lifetime. Then black cotton is also useful because of its electrical conductivity, and we can avoid electrostatic discharge. The inner layer used are these PoliMI plus polyester foams. Sorry. We made analysis using black cotton outer cover and then considering different inner layers. The blue and the green lines refer to the classic aluminous cathode, aluminous mirror we can find from reference, while the other lines are considering values coming from datasheet of official ESA supplier. We consider for the thermostructural calculation an heat flux coming from MLI, coming from the outside, and so passing through the MLI insulation of 2 watt per square meter. This value is the highest one, and this is done in order to have a robust design. So, considering the worst exposition case, I mean, when half of the telescope is irradiated from the sun, and considering a heat flux through MLI of 2 watt per square meter, we have this picture of thermal gradients. Thermal gradients are very, very little, and then we can guarantee a maximum longitudinal displacement of 0.43 millimeters. Lateral displacement of the structure are negligible because the lateral thermal gradients are very little. Now, considering the main bus and the sensor housing. As said before, there is heat generation due to components when they are active, and we need to maintain them in their operational temperature range. A pure passive control can be adopted considering 2 dedicated radiators from the main bus and from the sensor housing. The radiators are never exposed to the sun thanks to altitude, and then the hot and cold case are regulated in a passive way through heat switches. In particular, we can notice these are the internal generation in the worst cold and the worst hot case for the main bus and for the sensor housing. Sorry again. So, using a SimScape model, considering as no batteries, PDCU, and some internal components, the worst hot case is represented by these yellow lines. The worst cold case is represented by this purple line. These 2 lines represent the temperature we can guarantee in both hot and cold conditions. So the design is quite good because we can have also a margin with respect to the operational temperature for each component. Now I'll leave the stage to Simone for the details.
Good morning, everyone. I'm Simone Ferraboli, and I've been in charge of sizing the electric power subsystem. Now, the first input, the main input to the sizing of the EPS is the power budget. So that collects all the power required by all the components of the other subsystems. And as you can see, we reach quite a high amount of power during all the operational lifetime, with peaks of power of over 4 kilowatts. And I mean, considering that those 2 peaks are for the observation with one instrument or the other, if you remember before, we have over 80% of the time in which we're required this kind of power. And that's mainly the reason why you see here the power that our solar arrays can provide. And it's always above because we may be forced to also charge the batteries. And we may be forced to charge the batteries during the operational lifetime, and thus it could happen that we have batteries charging in this condition. Now, the main constraint is for sure the fact that we have to look basically everywhere in the sky, and this means that we must provide enough power for the observations of those peaks of power, no matter what the orientation of the space of the telescope. And I mean, we consider mainly 2 kinds of solutions, one with fixed solar arrays and the other one with solar arrays with mechanisms. And the fact that we realized pretty soon that having solar arrays with mechanism has a lot of benefits. For example, we can use smaller panels. We can always provide power no matter what the incidence angle with the incoming radiation. And but let's say the only kind of drawback that we have is the fact that we have a rotating mechanism. So we have something that may fail. But we actually took that into account, as we will see later. So we went for solar arrays with a drive mechanism, and we tried to go with a high TRL one because, of course, it's a very important component. And we completely neglected the possibility of an RTG because, well, having a European launcher for sure that doesn't allow for nuclear sources. And now this is the sizing of the solar arrays. So the main sizing modes are the observation mode, so the peak power, and the safe mode. Since the safe mode, for the safe mode, we may be forced to use the batteries in the worst conditions. And these are the parameters that we considered. And basically, just keep in mind, we decided to go with a 30-degree incidence angle as the sizing angle, even though we're pretty confident that we will stay way below that value. And we also considered the fact that solar rays, of course, will heat up. So we took a temperature of 150 degrees. And we arrived to a total area of around 13 square meters and a total cell mass of 25 kilograms. That's just for the cell. I mean, the structure will be discussed a little bit later. And again, for structural reason, we decided to go with 2 solar arrays divided in 3 panels each. And for each panel, we have this configuration of cells, so 66 cells in series and 20 strings in parallel. So each panel has dimensions of 2.4 meters times 2.1 meters. And panels, they provide a bus voltage of 70 volts. Now, as I said before, what happens if the mechanism fails? And just put things into perspective, this is the half sphere that our telescope can observe. We have here a 2 point right in the middle, and the telescope will observe in this direction, with this being the plane of the ecliptic. And as you can see now, basically, we have these pictures that are color coded. The green part is the part of the sky that we can observe, and in which we can also charge the batteries. Whereas the cyan one is the one where we can just observe, because our panel do not provide enough power also for battery charging. And the black one is where our solar rays cannot provide enough power due to the incidence angle being too large. So basically, as you can see, if we have no failures, we can look wherever we want. And these are 2 extreme cases. One with a failure at 0 degree inclination. You see we have only one region that is around 30 degrees in latitude and longitude, where we can observe and charge the batteries. Whereas we have a larger region where we can also we can just observe. And this is for a failure at 90 degrees. Now, the important thing that we can take from this analysis is the fact that even though we have a failure of the mechanism, that does not mean that the mission is over, because we can just reduce basically the field of view, meaning we cannot look everywhere, but still we can perform science. And then we're on with the batteries. As it's been mentioned before, for us the battery sizing is a little bit peculiar because of the fact that we will always have solar rays in light, so we will always exploit them for power generation. But it might happen that for some failures, we may be forced to go in safe mode without the batteries, without the solar rays providing power. And that's why we decided to go, and that's why the reason why we decided to size the batteries for safe mode, just to add a little bit of redundancy and to make sure that our spacecraft doesn't die if the solar rays are not working. So with that in mind, we had a total capacity of the batteries around 9,000 watts per hour with a mass of 57 kilograms, and their configuration is with 19 cells in series and 24 strings in parallel. And of course, we checked that we can also use those batteries for the deployment phase. So the phase will be at the beginning of the mission where we have to unfold the solar rays. And from the sizing, we got that. I mean, the amount of capacity we have is enough to guarantee also the deployment phase. And finally, this is a rough configuration for the EPS subsystem. Have the 2 solar arrays and the batteries that are connected with the PDCU. The PDCU mainly is in charge of controlling the incoming power, so we will have for sure 2 big power trackers for the power incoming from the solar arrays, and we will have some battery charge regulators. But also, for us, the PDCU must basically, since the incoming bus voltage is, as said before, 70 volts, the PDCU must convert the power, the voltage, in those 2 buses, one at 100 volts unregulated just for the reaction wheels, and then the 28 volt regulated bus for all the other components. And that's why basically we decided to go with 17, just because it's a middle ground between those two buses, and we want our power conversion to be pretty much the same efficiency. And of course, we're going to need probably some DC-DC converters for the components attached to this regulated bus. And you can see this is our mass budget for the EPS. We have mass of around 120 kilograms, considering a 10% margin for the measure. And the power budget just for the components that would work for the EPS is around 45 watts. And of course, that in case we have the batteries charging, we would have to add that the power required by the batteries. And that's it for the EPS. I'll leave the word to Serena. The structures.
Good morning, my name is Serena, and we'll talk about the structures. First of all, start with the requirements. Our main requirements come from the optics and the sensor, which has to fit at 12 meter focal length, and we have to guarantee the 3 meter diameter for the optics. Since there are no standard adapter from the Ariane to fit this size, we decided to use the ATD adapter. Since it has already been tested in launch, and for these in the table you can see the constraints that come from the launcher in terms of frequencies and geometry. For the sizing process, we decided to take into account the lift-off and the pressure oscillation solid rocket booster end of flight, since they are the most demanding cases in terms of maximum lateral load for the lift-off, which is of 2 Gs, and the maximum longitudinal loads for the pressure oscillation, which is of 6 Gs. Of course, a load safety factor for the acceptance levels. As a design choice, we choose to use the carbon epixel shell, since it has a really good properties in terms of density, stiffness, strength, and thermal stability, as already said by Simone. The rings we have added here and all along the bus are used to improve the stability of the shell and connect all the different shell, both from the bus to the telescope and inside the telescope, and to reduce the backing length. Since, as said by Pablo, we could have to stay in the, we could have to delay the launch, we choose the materials with low outgassing properties, with high performance in terms of outgassing, in such a way not to pollute the optics once we are in orbit. Okay, so for the film analysis, we have used the pattern master softwares. This is the 4-second mode, which is at 11.6 Hz nearly, so it's quite higher than the one allowed from the Ariane. The first lateral frequencies. Then we check the maximum displacement to be sure not to damage the structure and not to hit the walls of the Ariane in both cases. And then the backing factor, load factor is positive, well, greater than 1 in both cases, so no backing of course. And to test the properties of the composite to these loads, we use the optimum criterion. And since all the failure indices are lower than 1, we have no failure in the composite. Although there is a region here in which is closer to failure, but still the failure indices is really, really small. For the sizing of the solar arrays, we decide to use these layers. The one tested are only the structural ones, so the phase scheme in carbon fiber, the honeycomb in aluminum, and the phase scheme in carbon fiber on the thread. As said before, we decided to divide them 3 times for a total mass of 65 kilograms and first frequencies of 11.57 Hz. From the analysis, the model analysis, we saw that there are some frequencies that fall into the range of the acoustic frequencies coming from the Ariane, which means these are the center frequencies of the acoustic loads. Therefore, we need to test this structure and the way it is attached to the spacecraft to be sure it will not get damaged during the launch. So, Going back to the system level, this is the mass budget, the final mass budget. We have the payload, which takes into account both optics and sensors. The propellant, as said before, with a 15% margin. And this is the table of the dry mass with all the margins. We have higher margins for the telecommunication and VDH. The telecommunication because there could be changes in the antennas we want to use, and for the VDH because to take into account also all the cables in our component. So this is the total dry mass margin. If we want to exploit the Ariane 5 upper stage to go directly into L2, this is the maximum allowable mass with 80%, the 80% of the total. So our total mass with the margin is this one, and the launching mass taking into account the ATV adapter is 4 tons and 4. So we are able to launch. And then Pablo for the cost analysis.
Good morning again. I'm gonna talk now about the cost and risk analysis we performed. For the cost, we took into account the typical sections in which the space mission is divided. Of course, we have the maintenance and operation, deployment. With deployment, we have the launch and the system itself. For the system, we took into account the contractor fee and the cost to contractor, which includes the ground segment and the space segment. And in space segment we took into account the production, development, software, and RASP costs. So using the USCM model, you can see here and also here the values for the cost. The highest cost comes from the space segment, which is about $600 million, and the total cost is $1.4 billion, which is more or less €1 billion. Now I'm going to talk about the risk analysis. The main parameters we took into account for computing the risk was the probability of fail of a component, the severity of the fail, of course, and the fact that the component has or not redundancy. To compute the probability, we use the complexity of the component and the TRL that for Galaxy Ranger is always above 7. So you can see here a selection of the risk we took into account. I'm going to talk about this one and this one, the payload mechanism and the panel mechanism. The panel mechanism, as you could see, allows us to perform the mission but with lower field of view. So our recommendation to reduce this risk is to analyze if the mission or the feasibility of the mission with the reduced field of view we would have with the failure of the panels. And for the payload mechanism, which is the mechanism that moves from one sensor to the other, the risk is also above 4, but we recommend to perform a test to check for redundancy in the mechanism because we have also computed what will be the cost and the risk with the redundancy, and it will go below 4, so it will also be not that high. And then I'm gonna leave the word for the conclusion.
Thank you. Good morning again. Just a summary of the result of our study. So the mission is feasible because all components have high TRL, and then also the cost is reasonable. Weak points are related to the mechanism, in particular to the solar array ground mechanism for the reason explained in this presentation, and also the payload mechanism, so the possibility to change the payload. Also notice that the weak point could be the phase array, because a dedicated design must be done in the future. Possible tests and suggestions are, of course, the thermostructural test, because, as explained, the necessity to maintain the alignment between the optics as the sensor is fundamental for the mission. Then, the test must be done also for the acoustic loads, as explained by Cyril in his paper. Sorry. This is the team, and then a special thanks to these people. The presentation is finished. I hope you enjoy this presentation, and I want to thank you for your attention.
Or if you have questions for them?
Yeah, actually, I didn't see the possibility to use heaters for the structure stability. You don't get very good stability, just fill completely the gap along the structure.
Yes, this is an open point because it's necessary to have a precise detail of the whole structure. Of course, in Newton XMM mission, heaters were used to maintain the stability of the structure. And in this study, they have not been considered because a detailed study on MLI and thermostructural analysis, as done by us, were done. So, of course, ITERs can be used because of also for previous mission.
That was yes, I saw you considered 4 ground stations.
Yes.
Yes. So this often have a high impact on top, which is quite high. But okay.
Yes.
Just I wonder, did you consider, for example, compressed data in one verification only and same data, less frequency, just to save
Well, what we did was an analysis on the memory and the download time together. So what we saw was that the data were continuously increasing above the level that we showed in the presentation. So actually, we didn't also have information on the utilization of the ground stations. And what we did at the beginning was also to consider the Ka band to transmit with a larger bandwidth, so with a larger data rate. And what we know is that the technological level is not ready for this. Maybe for 2025 it could be taken into account for sure. But yes, since we have freedom, we choose 4 ground stations. Actually, it is possible to lower them a bit by changing the other input parameters. And I mean, this should be a trade-off on costs, maybe in a secondary level of the analysis, but it is possible.
Yes, no, I didn't see if in the thermal balance you have considered the optics of the heaters.
Yes. I consider a value of 800 watt for the optics, just as a reference, because this was the value used for Newton. I could not have a detailed analysis of the optics because of lack of information regarding, of course, the materials and then the particular structure. Because, of course, optics are the core of this mission. Their position, their thermal control, and their stability during time are vital for science purposes. And, of course, more information are needed in order to have a good design for this.
I have a question about the failure analysis of the sun. You consider only one of the solar wings stuck or both?
Well, basically, instead of having them rotating,
because
at a certain point,
we have 1 or 2 suns.
We have 1 for each array.
Okay, so let's say this is a very worst case that both are failing.
Yes. Yeah, that's the absolute.
Because I was wondering why the pattern was symmetric. In reality, I think a much more probable failure situation would be that one of the two is failing and the other one is still operating. So you shouldn't have a symmetric pattern of the half sphere.
Yeah,
so in reality, this is a very conservative and unlikely scenario.
But you know that engineers are not optimistic.
When they get older.
No. They have to start now not to be optimistic. So any other questions from the audience? So if this is not the case, I invite Professor Bernelli to provide the gift for the foreign students that I invite to come in the front. So thanks again for the Galaxy Rangers. The 3 foreign persons stay here and the rest of the team can go. And please give us
le modalità di visualizzazione per avere un dettaglio superiore di alcune immagini. Cioè, tipo,
come here, please.
Ok,
non viene più fuori, però comunque sta fuori non
Quite quickly, let's say.
So I apologize for the Italian students. have a gift for international students. This is a book on the history of the Italian achievements in space. It's written in Italian, but I'm sure that by now the international no. I hope you will bring it and diffuse the knowledge of the Italian space.
So we can have the Mozart now. So the last group that we will see today is related with the with the lunar sample return. Sorry for that. The Mozart mission, and enjoy our last presentation. Yeah.
No, aspetta, questo è questo qua.
Scusa, non è sempre
Good morning, everyone. I am Leonardo Bora, and I've been the team leader of Mozart in these last 3 weeks of works. Mozart is an acronym that stands for Moon Sample Return, and this is briefly what we are going to present you in this hour, and I hope you will enjoy. So our mission primary objectives are to sample, collect, store volatile samples to be brought back to Earth, and meanwhile to analyze also other properties at the surface of the Moon. Mission requirements are related to launch with an European launcher, preferably, and to stay more than 6 months on the surface, and to do this operation in the South Pole, far side of the Moon. And moreover, the return mass, the mass that must be returned to Earth, should be in around 100 grams. Why volatiles? Volatiles are important because they can help in the study about the formation of the solar system. And moreover, they are of interest for future in situ resources utilization on the Moon. And it's believed that they are trapped inside volcanic gases on the lunar rocks. And mainly from this, as we can see from this picture, we can see that they are mainly distributed inside craters. And this is, of course, the area limited around the South Pole region. Some aspects of about the environment that we have considered. Mainly we focalized in deep space environment and the environment that we can encounter in the Moon. But what we mainly focused on was the very low temperature that you can find inside the craters, and the fact that there is no illumination at all. So, mainly related to the fact that we are looking volatiles, and we want to be sure that where we land there are these volatiles, we decided to land inside the crater. And among all the craters that are present in the South Pole, we choose this one because it answers the requirements of being in the South Pole and in the far side of the Moon. It's quite deep, 4 kilometers. So inside it's completely shadowed, as you can see from the picture, And this is good since there is no risk that the volatiles, the rocks, are polluted by solar radiation. And moreover, it's appropriate for a landing since it's quite wide in diameter, around 21 kilometers, and it has an average slope of 30 degrees. These are some operations that we considered in order to decide our mission architecture. In fact, we analyzed if it was better after having entered in the crater to jump out to reach a peak of light that are near Shackleton. We also analyzed if to dock the sample when it's before coming back to Earth or not to dock. We analyzed if to have a rover or not, mainly to explore more areas inside the crater. But we decided at the end not to jump out, to dock, and not to have a rover, mainly because of mass issues. And so our final architecture is to have an orbiter, a lander, a re-entry vehicle which is composed of a service module and a re-entry capsule, and an ascent vehicle from the moon. And of course there is also the chaser, but the chaser is not another vehicle, but it's just the orbiter and the re-entry vehicle together, back to the docking. Sorry. This is briefly our mission timeline. After the launch and the injection into the lunar polar orbit, the chaser and the lander will unlock, and the lander will perform a soft landing inside the crater, and it will the sampling operation will be started, and they will take around 2 days. And after this time, the sample will be launched back in the lunar orbit. It will dock with the chaser. After this, the orbiter and the re-entry module will undock. The re-entry module will come back to Earth and will release the re-entry capsule in the atmosphere. Meanwhile, all this will take around 10 days. Meanwhile, the operation will continue on the surface of the moon for the rest required times, and the orbiter too will continue to orbit around the moon for telecommunication, mainly for telecommunication tasks. And now I leave the stage to Mohit, who will talk to you about configuration.
Thank you. Okay. The configuration, the main driver for configuration is basically to allow the simplicity of the design and also keep in mind the different requirements we have in terms of technical and also physical, in terms of the constraints which the mission allows us to project. So the composite, due to the complexity of the mission in terms of going to the far side of the moon and to be able to land in an inaccessible zone in terms of difficulty in communication and difficulty in direct sunlight, since the place hasn't seen sunlight in ever since it was there. The composite has been divided into several different smaller parts. The lander, the orbiter, and the re-entry module, which contains the capsule itself. So, as we see, the center of mass has been concentrated on the lower part of the structure, which includes the entire composite itself, being 5 meters, and the ground coverage is 3.4 meters square. The main driver, as we said, that since it has to perform different functionalities, it has been divided into some sections, and at different points in time during the phase mission, as we see in the timeline, it has to do some deployments and it has to do some detachments from the entire composite.
which we'll go through in the next few slides. This is a visual image of what is actually happening during the different phases of the mission with respect to the entire composite. So we launch the entire system up to the polar orbit around the moon. At that point, after it has reached the desired height, altitude above the surface, the detachment of the lander takes place. The mechanisms are very simple with high technology readiness levels. And it uses simple Marmon clamps, which are under tensile strength. So they release upon the sensor being activated. So after this has happened, also at this point there's one more mechanism which takes place. Is the as we see in the previous slide, we've got external tanks attached on the side there. These external tanks are used for the powered cruise, and at the point where we detach, the external tanks are also jettisoned out. Next comes after the sample has been contained within the launch missile, and it has been stored in the sample capsule. It has to be helped to dock with the main re-entry module, which is what comes back to Earth, containing the sample. So again, here we've got a simple spring mass system, which allows the capsule to be released and projected towards the trajectory of the re-entry module itself, such that the docking is taking place with the maximum chance of getting the probability right. And the final one, just before the atmospheric re-entry back into the Earth, so there is another small detachment maneuver with the same concept as used for the initial one. Here we've got the Marmon clamps again for the detachment of the re-entry capsule with respect to the re-entry module, which contains most of the electronics and also the body-mounted solar panels. The next few slides, I'll just go through each model configuration very briefly in order to understand what is the components which are contained within them and what were the different functionalities which allowed us to conceive this particular idea of the composite structure. So this is the structure of the lander. We've got the face which is doing the drilling with the driller and the robotic arm, which allows the disk to contain the sample itself. Then we've got the top view. The main driver, I must mention, is the size of the propellant system within the tank, which is only used during the landing phase. So the volume contained within this and the mass requirements actually drove the dimensions of the entire lander itself. We also notice that there is a truss structure here, which allows to minimize the mass and be able to distribute the forces consistently during the worst conditions of launch dynamics. We've got the nozzles here, and finally also we should mention the lander rotation mechanism, which would be in the later part for robotics, which basically concerns with the rotation of the lander with respect to the moon surface to allow better chance of the drilling. And moving on to the re-entry module, we've got which is basically mounted on top of the lander during the initial launch configuration. It contains a simple hinge joint which opens to allow for the docking procedure to take place. And also here, if this is the internal structure which is being covered by the solar panels and the orbital truss itself. 4 ADCS thrusters placed attitude dynamics control to control the maneuvers which are related to station keeping and also be able to allow for better communication with the lander while orbiting the polar region of the moon. Then Okay, moving on, the orbiter itself, we've got deployable solar panels, which are folded at roughly an angle of 120, so that they mount exactly on the surface uh, of the orbiter face here, and immediately upon the launch release from the launch vehicle Delta 4 in our case, it is deployed, and the deployment mechanism is using simple servers and actuator motor system, which allows it to open up and also rotate in two different axes to be able to point to the direction of the sunlight. Last thing to mention would be the interconnection, because this part is the top view of the orbiter, which is connected to the bottom part of the re-entry module. So we've got a clamped space here, and it allows to detach once the docking has been taken place with the sample capsule, and the re-entry module is basically ready to get back to and make its way back to Earth. Over to robotics to explain the details of the drilling mechanism.
I'm Carlo Buzzi, and I'm in charge of the robotic subsystem. So the primary objective of the mission is to bring back to Earth a sample return mass at least of 100 grams. And this sample has to be in pristine condition in terms of temperature, pressure, physical integrity, and contamination. In this table, we can see the different phases of the robotic subsystem and their interaction with these four parameters of the sample. It is important to consider during the drilling and sampling operation to avoid an overheat of the ground in order to avoid sublimation of volatiles and guarantee the integrity of the sample. And during the sample operation that regards all the re-entry phase, it is important to keep the temperature in a fixed range in order to limit the phase change of the sample and avoid or limit as much as possible the leakage. So here we have a video that shows the operations. We can see so that there are two drilling operations that are performed. The first one, and then to make the second one, there is a rotation of the upper part of the lander respect to the legs. So the operation ends when the sphere is launched from the lunar surface. So for the drill, the main drivers that have been considered are the thermal problem. So as said before, not to overheat volatiles, the power required, so minimize the power, and also time is important since the first launch window is less than 2 days after the landing on the moon. So has been designed a single rod rotary drill with shutters. In this sketch we can see the bit in drilling mode and sampling mode. So we can see that in sampling mode, the main bit is retracted. The drill rotates. In this way, creates the sample core is created, and at a certain height, a shutter mechanism detach the sample from the ground. So the primary solution that has been chosen has been performed some calculation considering the soil made of basalt. So we have a cutting speed of 2.5 millimeters per minute and 25 RPM. Power required at 29 watt, and the time to reach the sampling depth of 1 meter is 400 minutes. In this graph, we can see we have studied the thermal problem. So this graph shows the overheat of the soil due to the drilling operation. Has been assumed initial soil temperature of 40 Kelvin and an ice soil made of water. This is the point where at the time we reached the sampling depth. This drilling condition avoid the sublimation of volatiles, since in lunar condition the temperature of sublimation of water is 200 Kelvin and of CO2 is 140. There is also a backup solution where basically all the drilling parameters have been doubled, but we see that the most important driver is the thermal one. So in this case we have an overheat of 40 Kelvin, but also in this case we avoid the sublimation of volatiles. Regarding the handling system, the drivers are the reliability of the system. In particular, try to have the simplest motion in order to minimize the degree of freedom and limit the number of motion in order to minimize the possibility of a failure. And also lunar dust is important, since we have to protect mechanical and electrical device in order to avoid a jam of the system. So has been designed a robotic arm with a plate fixed on it. The output of this design is in terms of geometry and mechanical properties. In this picture we can see so that we have 3 degrees of freedom, a translational gear, and we have 2 rotation here and here along the azimuth axis. We have 2 arms, and on the second one we have the plate fixed on the second arm. In this plate, I'll show later, there are the sample container, and the drill delivers the sample in this plate. So the dimension of the sample are height of 10 centimeters and a diameter of 3 centimeters. The sample container is 12 centimeters in height and 3.5 in diameter. Here there is a sketch of the sample mechanism, of the sealing mechanism of the sample container. Basically, the cap is pushed against the sample container, and due to an elastic deformation, here is a section of a ring and these harpoons, they attach the sample container. I've been choosing this solution with respect to other sealing mechanism that use maybe an overheat some elements. Another important point is the interface between the launcher and the sphere. Since once the sphere has been launched, at a certain point, the sphere and the rocket have to be detached. So we have an external ring attached to the sphere. We have an interface that ends with 2 hooks that are attached the ring on the sphere. And at a certain point, these hooks are detached from the ring, and there's a loaded spring that separates the 2 elements. In general, in order to reduce mass, power, and complexity of the system, a passive control of the sample has been designed. In the first figure, we can see the design of the plate. So we can see that this is the sample container. The sample container is inside runners. This in order to guarantee the stability of the sample container, and they are placed on an insulation made of thermal washer. Then the runners are surrounded with aerogel, since it has good structural and thermal properties. Here we have other 2 sealing mechanisms. In the upper part of the sphere we have a cylindrical chamber, and it's important to say that the operative temperature of the plate is 140 Kelvin. And it's also important to consider temperature and pressure sensor inside the plate in order to monitor the samples during the re-entry phase. This also for further analysis made on Earth. Here there is the delivery of the plate in the sphere thanks to these 2 lateral joints that are inserted in the lower part of the sphere. We can see a tank that contains a gas, in particular has been chosen helium. And once the plate is in the sphere, we can see that an increasing of temperature, the gas causes an increasing of pressure. So there are 2 valves here that at a fixed value of pressure are open unless the gas flow in the cylindrical chamber. This is important for two aspects. The first one, because the pressure of the gas helps the sealing mechanism of the runner, and the second one is for leakage. Since if we have a sublimation of volatiles and we have a leakage in the first and the second sealing mechanism, volatiles are mixed with this gas, and so once the sphere is back to Earth, scientists could recover the plate, and knowing the gas that is put in the sphere, they could recognize the lunar element. There are also other two valves put in the upper part of this chamber for a security reason. Since if you have a overpressure due to an increase of temperature, these valves are open and the gas flows in the upper part of the sphere in order to reduce the pressure inside. So we have the mass budget of the robotic, considering drilling handling system on the sphere, is 20 kilograms with a 20% margin, and the power budget is of 38 watts. Some criticalities that have been taken into account during the design are the pollution of the landing site. So has been designed as sampling, has been chosen a sampling depth of 1 meter. Overpressure of the sphere, as just seen, we put valve to reduce the pressure in the sphere, and a critical drilling point. So we design a rotation mechanism in order to change the drilling point if the one chosen is critical due to rocks or the solids to earth. And now I leave to my colleague Matsubian.
Good morning. Sorry. So, well, we depart from the Earth the 24th of February, following a direct transfer, and we arrive at the sphere of interest of the Moon after 3.6 days. This direct transfer has been selected after a comparison between a low energy transfer, but the first delta V that we found was height and comparable with the one of the direct transfer, so we chose the simpler and the quicker solution. Once the satellite is in the sphere of influence of the Moon, we have to close the entry hyperbola, and we inject in a elliptical orbit in order to split the delta V required for the injection in the operative circular orbit. The inclination is about 90 degrees in order to be visible, in order to make visible the satellite, the lander in the crater, and the run of the orbit is 60 degrees because this allows us to minimize the delta V cost. So the orbiter now is in the orbit around the Moon. Just before the orbiter arrives at the North Pole, it begins the descent phase. So the lander detaches from the entire vehicle and begins the orbiting toward the South Pole. Here he begins a power descent when it reaches 7.7 kilometers from the ground, and when the lander is in the crater at an altitude of about 100 meters, it keeps the velocity constant with a value of 1 meter per second in order to allow the radar detection system to understand the morphology of the ground and allow the shift accordingly. You can see We can see the thrust and the horizontal and vertical velocity for the power descending, and here for the other avoidance, the horizontal displacement. After 1.43 days, we have to launch our sphere containing the rock sample. We use a rocket that will bring the sphere in an orbit that is an height of 105 kilometers, so above the one of in which there is the orbiter and also the chaser. The trajectory is divided into 4 phases: a vertical ascent, a coastal turnover, after which the rocket injects in orbit with apocenter tangent to the circular orbit, and here make a final impulse. You can see that the inclination and the run of this orbit is the same of the Caesar one. The sphere of mass is about 10 kilos, and the overall mass is 48 kilos. Now we have performed the rendezvous and docking. That is made of 3 phases. You can see here the overall trajectory, and now I explain the 3 phases. The first delta V injects us in a branch that allows us to minimize the distance from the V bar axis. Then a second delta V bring us on this branch that bring us to near the sphere. This is the final approach, after which we can perform a final translation. This translation is made only by RCS and not with main thruster, because the delta V required are low. So we can reach the sphere. For the reentry, now after the incubation of the sphere, the chaser detached from the orbit, which remains orbiting around the moon for other 6 months, and so the chaser go back to the Earth, following a strategy similar for the outward transfer. So we use a little orbiter to speed the delta V, and there is a 0 delta V on the sphere of interest, and we return to the Earth ballistically. Here we can see the phases of the atmosphere entry and eventually the splashdown after 23 minutes. Here we see the acceleration peaks that are below the 40 meters per second square. And here there is the landing site nearby the Australia in a navigated area. This is simply a summary of the delta V we need for the outward route, the return, and the maneuvers in between. This for the different vehicles. And since we need to use RTG, we can't use European launchers, and driven by satellite mass and sea energy, we chose the Delta 4 medium as a launcher. Now Antonino Pinzotta will speak about propulsion.
Good morning. I want to present a brief overview of the propulsion system. And I started from the general requirements, which are common for all the vehicles we have in the configuration, in the composite. For the lander, we need also immutability, total impulse, while orbiter need only total pulse number. The SN vehicle need a fine orbit injection and to work also at low temperatures, because if there is a leakage in the thermal system, we want to do the return anyway. And the reentry module basically has the same sub-requirements of the lander system. To select the appropriate system for every vehicle, parametric analysis related with mass and delta V and delta V's being performed with the idea to reduce mass and also power, because power is demanding also for the mass budget. Ending up with this solution: bipropellant for lander, monopropellant for the orbiter, which is light, solid composite for the ascent vehicle, after comparison with the bipropellant system that gives us a really lighter mass, and dual mode for the reentry module with hydrazine and MMH and TO system. All the propellant masses are marginal by 11%. Here there is the architecture of the lander during the cruise phase. It is this one, and we have a line that is in common for the landing, because we want always to reduce mass, so we exploit the propulsion system of the lander, both for first orbital maneuvers and for the landing phase. Yes. Here we have two branches for the feeding system, because as we said before, we want to jettison the propellant tanks, so I had to split those two lines. Here basically this is the feeding line for the power descent on the moon soil that relates, as I said, on the same propulsion unit for the cruise phase. Here you can see some masses and power demands, and here there is the architecture of the orbiter. That is a simple monopropellant architecture, so it's the simpler system above all the vehicles. It is has been selected because it's so lightweight, the monopropellant solution with the small orbiter, that all the weight we saved is translated in propellant mass. And here some information about the launcher, some numerical information about the launcher from the moon. That is a solid propellant based on composite propellants with two different grains with the diaphragm inside, because we need to ignite the first grain, then have a vertical ascent and a steering, let the system fly inertially, and then ignite the second grain after the breaking of the diaphragm, in order to have the orbit injection. And the system selected for the TVC is cold gas 1, because it assures good precision during the emission phase and also during the steering. Then for other features, I want to exploit maybe a composite case in order always to save masses, because the system is also small and it's easily built. Here the final architecture of the reentry module. most complex because it's the dual mode one. That is a branch for the RCS and branch for the main propulsion. The selection of the two different systems is related with the needs that are I delta V for the range of phase because we need around 800 meter per second, and low thrust RCS for the altitude control. And when we use bipropellant, it's not possible to have so low thrust levels. And for the general architectures, that's all. I leave the floor to Gabriele.
Good morning, I'm Gabriele Contucci and I will talk about the onboard data handling subsystem. The requirements we have identified for the subsystem are to manage and store the data produced by the telemetry and the scientific payload, to give the lander the ability to perform autonomously the hazard avoidance maneuver during the final phase on the landing, and to give to the chaser the ability to complete in a semi-autonomously manner all the maneuvers and all the maneuvers to catch to complete the docking. In order to size the memory on board, two things have to be taken into account. First, the amount of data produced per second, and then the frequency of the download of this data. Trade-off between two different strategies has been done. The strategies was to download very often the data. And this is as an advantage the fact that the power and the mass of the memory unit will be low, and also the fact that the scientific data will be available very soon. But as a disadvantage, the fact that a high number of maneuvers to point the antennas backward will be necessary during the lifetime of the mission, so a lot of fuel will be necessary. The other strategy is the one opposite to the first one, because the idea was to accumulate a high amount of data and then download this data every couple of weeks in a long window. This has as advantage the fact that the number of maneuvers required will be low, so there will be less fuel necessary. But the disadvantage will be that higher power and higher mass for the memory unit, and then the scientific data will be available after a while. So the choice done was to have daily communication between the orbiter and the lander, since the antenna mounted, as we will say, after going doesn't require a very high precision. So the maneuvers necessary are not so demanding. The data produced has been estimated between the scientific data and the telemetry around 41 gigabyte per day. So as we consider to install in the lander a 128 gigabyte memory, in order to take into account possible increases in the scientific data produced by the payload. While for the scientific payload, the communication between orbiter and Earth, the frequency has been chosen. The download will happen on a weekly basis. So the total data produced by the telemetry and received from the lander has been estimated around 240 gigabytes per week. And then 1.2 terabyte memory has been installed in order to have the possibility to install further scientific payload on the orbiter if it was possible. Then for the docking and the landing, the two phases are very similar, because in both cases high amount of data that will be produced by the camera installed must be analyzed and then capacity analyzed in the smallest amount of time possible in order to give to the control system the changes needed to perform the operation. In order to cope with these requirements, it has been assumed that a dedicated hardware will be installed on both the lander and the orbiter. Here we can see the architecture for the orbiter with the relative mass and power budget, and then the same can be seen for the lander. To conclude, the requirements of the storage and management of the data has been decided through a choice of an appropriate download strategy. And then for the docking and the re-entry, we chosen to install a data processing tool. Now I leave the stage to
Hi, all, my name is Paul. I'll talk about the TNT subsystem. Okay, so the main requirement of the TNT subsystem is to provide the links for each phase of the mission. And our driver for the design was to guarantee the availability and reliability of those links, but also provide redundancy in case of failure. And because of the fact that the TNT subsystem interfaces with some other subsystem, like the power generator subsystem and also the software subsystem, we had some constraint. Okay, that was to reduce the mass and power consumption, but also reduce the pointing constraint of the antenna. Okay, now we did a study on the visibility between the spacecraft and the ground segment during the operative phase, and those are the assumptions of the study. In fact, according to that result, we decided we choose a communication strategy during the operative phase. That would be to communicate with the lander, as my colleague says, for 7 days, and after, therefore, air pointing maneuver and communicate with the ground segment for 24 hours. And we also perform visibility study between the lander and the orbiter. We consider the worst case, where we have our lander in the crater, in the middle of the crater, and no dimension of the crater and attitude of the orbiter. We calculate the maximum field of view between both of them, and we also calculated the visibility period between the lander and the orbiter, which is approximately 39 minutes. And after we choose the band that we will use among all the possible bands, and also we decided what will be our ground station, and you can have here the ground station of the coordinator. Okay. Here you have the configuration. Okay, so as the configuration, we decided to use one high-gain antenna that will be mounted on the orbiter, two low-gain antenna, one will be mounted on the orbiter, and the other one will be mounted on the lander, and will communicate together. And one omnidirectional antenna that will be used during the re-entry phase. Here you have for each phase of the mission the different antenna involved, the type of data exchange, the volume of data, and also the data rate required. Here, for example, you can see that the communication between the lander and the orbiter, the data are telemetry and scientific data from the lander. And as my colleague said, we communicate with the lander for 7 days. So the data rate here is 434 gigabit. You can note that the data rate double with respect to what my colleague says because we use the encoding system. And for the communication between the orbiter and the ground segment, okay, here you can see that the data change because we add also the telemetry data produced by the orbiter, and then the visibility time is 24 hours. Data rate is 5.5 megabit per second. We also did the same thing for the communication during the re-entry phase. And here you have the link budget. Okay, first of all, I have to say that we perform the link budget only for the downlink phase because it is the most stringent in terms of power, in terms of required power. And the procedure to calculate the link budget was this one. First of all, we fix the big error rate for the downlink at 10 at the power minus 5. It means that the probability to have one wrong bit among 10 advisory transmitted. So we thought that it is a very good literate for the downlink phase. And after we choose the modulation technique and calculate the signal ratio required for the link. And with the new project equation, we performed calculation and we had all those other values. Okay, as you can see here, we highlighted the input power required for each link and also the mass. We have to can carry on. Okay. Okay. So those are the last two links, and we do the same thing. And here you have the architecture of the orbiter. As one of the most important requirement was to provide also the redundancies in case of failure. Here you can see that on the orbiter we have two antennas, the Hagen antenna and Logan antenna. And we did the redundancy in the reception line because we thought that in case of failure, for example, in the emission line of the Hagen antenna, we could still use the Logan antenna to communicate in the ground segment, but with very low data rate. So, and vice versa. While here, for the communication for the lander and the orbiter, and we had only, as we had only one antenna on this vehicle, we did the redundancies in the transmission line, but also in the receiving line in order to guarantee the affordability and the flow redundancy. And here we have the mass and power budget for each vehicle, for each phase of the emission. As you can see here, the greatest power required is by the Hagen antenna during the emission operating phase. It is 45 watt, which is highly affordable by the power generation subsystems, and also the mass. So we can conclude that we respect our constraint. So now I'll pass you my colleague Leonardo.
So regarding the attitude determination and control, the sizing operation for lander, orbiter, and reentry, you can see the second column on this table. And basically for the lander is the hazard detection avoidance maneuvers, so the lever maneuver. For the orbiter and the reentry is the docking while they are in chaser configuration. And for lander, orbiter, and reentry module, the only architecture possible to accomplish all their operation is three-axis control. While for the ascent vehicle, control the only control is over two axes. And for the lander, so as I said, the sizing maneuver is the one to happen while we want the levers maneuver, and from mission analysis, that maneuver sized would require to make a 45 degrees view in less than 5 seconds. And with the thrusters selected together with the propulsion colleague, we would have a performance below this limit. Moreover, the inertias have been estimated taking the wet mass of the lander to be conservative in the size. Here in the left, you can see the mass budget for the lander, and it has been driven by mass issue by mass reduction. And while during the descending phase, the attitude will be determined by a star tracker during the orbiting phase, by a minimum during the power descent, while at the end we will use, when we are above 100 meters from the ground, we will start using the cameras and other altimeters. Of course, camera will be working with the soil illuminated by LED lights, otherwise it would be impossible. For the chaser, of course, the sizing maneuver is the docking, and in particular the fact that we want to quickly scan the sky and make a fast view sized one fast zero to 180 degrees to happen in less than 30 seconds. That could be required when we are 400 meters beyond far from the target. Sorry, and with with just the control thrusters in the re-entry module, we would have this performance. And I have taken into account here the fact that the shield is open, and so this performance has been computed with the shield open. That is quite a big disturbance for the inertial property of the system. While the idea is to use instead the controllers of the orbiter for the final pointing of the docking sensor, which is the most demanding pointing we have in all our mission. So orbiter and re-entry module are not sized for their operations, and they are sized for the docking, but that sizing answers also their needs during other phases of the mission. Orbiter is just is basically a data link. So since the antennas are not so thin beamwidth, we don't have to make such an accurate pointing during telecommunication. The only accurate pointing we could have is in case we imagine to have more science mission added in the orbiter, but it's not a primary objective of the mission. In any case, the thrusters selected would be fine for this task and would not require an high amount of propellant. Always thinking that our mission is planned to last 6 months and not years. For the re-entry module, the most demanding task is to counteract the disturbance coming from the main engine while it's switched on. And here you can see a mass budget both for the orbiter and for the lander, for the re-entry module. Sorry. Finally, architectures. Here you can see the architecture for lander, orbiter, and the re-entry module. We see that the architecture are standard. They all rely on star trackers and sensors. And of course, there are dedicated payloads, as I've told you, for the hazard avoidance maneuvers, so camera and radar altimeter. While the sensor for the docking, which is a lidar, it's put inside the re-entry capsule, and it's not connected to the onboard computer of the re-entry module, but of the orbiter, since it's the orbiter who commands during the docking operations. And the horizon sensor has been built in order to have more accuracy in determining the fly path angle while before entering in the atmosphere for the ballistic re-entry, since the fly path angle is the most important thing for that kind of maneuver. And now I leave you to David, who will explain the control system.
The aim of the thermocontrol system is to maintain the temperature of all the components in their ranges. The design is driven by the hot and cold case, which represent the two opposite extreme conditions. For all vehicles, the hot case is found here above the moon subsolar point at 100 kilometer altitude, where due to the high temperature of the moon, there is a high value of the infrared radiation. On the other side, in eclipse, the temperature of the moon is quite low and the value of the infrared is quite limited. Different design were find a solution for the three vehicles. For what concerns the lander make use of the waste heat coming from the MRTG. MRTG produces 2,000 watt of waste thermal power. A part of it is exchanged with a hot plate, which is placed external on the lander faces. between the hot plate and the internal structure, it switch that controls the flow, and then there is the delivering to all the internal components. To help the rejection of it during off condition, there is a louvre placed nearby the electronics box, and the rest of the system is covered by the MLI, with also the external tanks and the atoms. These are the result of the multi-node analysis with the SimScape. For the orbiter is mainly covered by the MLI of all phases, except for the yaw phase, which is almost entirely covered by the louvre, that helps to control the heat rejected to the ellipse space. The louvre must not point the moon above the day side due to the high infrared of the moon, so it has been put on the opposite side of the moon direction, so it's zenith point. Anyway, it has been imagined to resist at 45, statically 45 degrees of the sun radiation. For the re-entry module, the problem was to isolate as much as possible the internal component before the detachment, because they are switched off, and then to create a path to reject the heat. This is a section of the base of the re-entry module. A part of the base is used as a radiating surface connected to between the electronics and the registry. There is a heat switch. During all condition, when the re-entry module is still attached to the orbiter, here this phase is covered by the orbiter upper phase, so there is no the heat leaks is reduced. When after the detachment, electronics is switched on, and then there is the path to conduct heat. Anyway, for cold condition, a little bit of thermal power must be provided, and this power for the re-entry module is provided by a higher depth of discharge of the secondary battery, which lasts just for the few days we do our task. Now we will stay electrical.
Good morning. Speaking about the electric power subsystem, we start from the orbiter, and the orbiter provides the power not only to its own payload in terms of power demand, but also to the payload of the other two vehicles, which are the re-entry module and the lander when they are all attached. The main driver to size the solar panels is the lunar operational, which of course when the orbiter is in its orbit around the moon, it performs telecommunications or some additional science at the time. And the driver to size the secondary batteries is the eclipse mode, which of course when the orbiter is in eclipse, they are the more frequent modes, of course. And in order to be robust, the solar panels are sized according to a spectacle angle of 40 degrees. And also we have added two solar plate drivers in order to optimize the orientation with respect to the sun. For the secondary batteries, we considered one eclipse per orbit. So we have this low depth of discharge, which is a good redundancy in case of extra power demand. We also use a small package of primary batteries for the first phase, which is the deployment of the solar rays. And we use a low power control unit. Here it's the sketch of the power plant for the orbiter. The dashed lines connect the power control unit of the orbiter to the loads of the two other vehicles, and are reported also the mass budget and the power demand of the EPS itself. The mass has been margin of the 10% in order to arrive to 23 kilos, and the maximum power demand of the EPS, of course, during the lunar operating phase, we must charge secondary batteries, and for this reason is very high, 159 watts, because we have not so much time in order to recharge them. And for the lander, as we have already said, we exploit the MMRTG. and it supplies enough power for all the operations on the ground, but for the descent, we need to use primary batteries, high energy density primary batteries, and also here we use a low power control unit. Here again is the landed power scheme. Here the mass budget of course is very high, 53 kilos, because we have an MTG which is very massive, and the maximum power demand from the EPS, of course during the power descent, because the power control unit consumes consumption is in function of the input power which we must provide. And we end with the re-entry vehicle. The driver, of course, is the inertial cruise because it's the much lasting mode, but we have body mounted solar arrays for a total length of 60 centimeters. And we need also a small package of secondary batteries, lithium ion, always high energy density, in order to provide enough energy to sustain the peaks of the powered cruise and the communication phase of the re-entry vehicle. This phase lasts a few minutes, but in order to be robust, the batteries are sized in order to provide this extra power for 1 hour. And here again, the re-entry vehicle power scheme, and the total mass of the EPS is margined, of course, 13 kilos, and the maximum power demand, of course, during the inertial cruise, with the assumption of charging the batteries continuously with 10 watt, but it's just to be robust enough. And now I leave the ground to Mohit with the structure.
Yeah, this is the final subsystem. I'll quickly run through the most important aspects. No intentions to take over your lunchtime, so sorry about that. The structure materials is okay. The first thing, aluminium 7000 series, tested for aerospace applications. So the first choice for us, most preferred. Also in the chart we see it's right on top with respect to the strength to density ratio. The basic internal model of the truss structure we have, including the margin, we put 200 kilos approximately, about 30% margin, and we applied, this is the Delta 4 adapter, applying the constraints to do the launch analysis. The results were quite satisfying, even though we have considered a very pessimistic point of view. Okay, the shear stresses which come mostly the green area, which is a good go sign. The most focus still brings in the middle part, which is the orbiter for us during the launch. Due to the thin shell structures, we do observe some rigid body motion, and also this would be covered in the modal analysis or frequency response, which does say that there is considerable movement during the launch dynamics, but still the good news is that it is still under the limits of the structure and the way it has been modeled in the entire composite. So far is so good. The displacement, nothing to be worried about. Looking at the red big box on the top, the maximum displacement still is just over 1 centimeters, which is almost negligible as compared to the 5 meters of the entire structure. So, and also we should keep in mind this is a local displacement while doing the applying the pressures and the loads for the launch, which by the way is a pessimistic 6.5 G for our case. Finally, the equivalent one misses stress, we've got about 230 megapascals of stress in our case. Again, most of it is concentrated in the orbiter and the interface between the orbiter and the lander. But the good thing to note is that for our case 70-75 aluminium, which we have considered, the yield stress has a maximum limit of 560 megapascals. Over to just give the conclusions.
These are the mass budgets for all the vehicles. In particular, here you can see for the re-entry vehicle, with all the margin applied by each of us for their subsystems, and we end up with a total margin wet mass of that you can read here. The wet mass of the casting vehicle. Here you can see the same for the lander, and it's of course the more massive vehicle of our architecture. And here for the orbiter, as you can see, it's not so heavy. So totally, with the 20% margin applied, we are around 27 hundredths of kilos. And since the launcher capability is in around 4 tons, we can say that we stay quite beyond the limits. So this is fine. And concluding, the output of our study is that the mission is feasible. There is also the possibility of for additional science over what is our main objective, and it can be done both on the orbiter and in the lander. For this sake, we have thought of some additional mass in our mass budget, both in the orbiter and in the lander. And main problem solved for the primary objective was the sampling. So the fact that we would have polluted the landing site with thrusters has been solved with the fact that we are drilling at depth of 1 meter. But still remain some open points, like the fact that we haven't analyzed the joints protection from lunar dust, which knows that is a big issue because it's charged. It should be verified, the landing strategy taken into account, maybe with some tests to be done on ground. The TRL of the scientific payload to answer the other mission objective, like to measure plasma and electric field at the surface of the moon, also dust, and to do radio astronomy is low. And also the guiding navigation system during docking should still to be much more studied in detail. Thank you for your attention.
So if there is any question for...
I saw a nice diagram before showing the sample that has been raised during the sample preparation. Was that referring only to the system during action?
Yes. I made the assumption in the worst case that all the power required goes into
Did you consider also to use the support of a hammer immersion, hammer, because that may help in reducing that risk that for this type of mission gives a peculiar requirement?
I consider it, but yes.
In the computation, just the drilling, the rotary drilling has been taken into account.
Because you put in some evaluation, you can add the reality and the immersion.
Thank you for the suggestion.
I saw you were proposing the infrared sensor for the entry phase. Is this something you have thought of? Is it the standard practice? Because I was wondering how is it that the infrared sensor optimized for the very lights of the descent, and isn't it affected by the aerodynamic duties of the variant?
We have thought to not use it while inside the atmosphere, but before the capsule is released from the service model.
So my concern is what is the range of altitude I'm taking to use the sensor, and is it operable in a range of altitudes?
It's low Earth altitude. We are the computation for the re-entry dynamics starts from 200 kilometers above the ground. So we are considering that the capsule is released at the date. So the determination of the angle of attack is done before. So in lower orbit.
If you have any other question also for the other groups that are in the rear that can come, yeah, you can get me. So also the Harmonia and the Galaxy. You know, if you have questions for all of them, I mean, still for the Motras, but they are followed. So, almost all of them. So, if you have any, just address it.
Maybe a general question on margins. Margins for the mass computation. Okay, normally this is, let's say, you apply to type of margin. One is maturity margin, combined system margin again. Sometimes I saw many times using 5-10% margin on mass. Okay, this is maybe easy for acceptable because the component is already available as is. As soon as you maybe need some customization of the component, that is a little bit difficult to maintain. The suggestion is that in these phases, phase A, phase A, and so on, to keep maybe 20% margin.
Be open to hearing.
Guideline that depends on this category. They could apply the following BCSS.
They try the most to stay in the address of the CSS as far as it's possible, of course, because they have to survive with the CSS for the rest of their life.
But I think there's a very good analysis because I don't know if just to speak in the past, because I have some years now. I don't know if in the past students at the end of the course were able to basically to let's say handle in a kind of overview. It's not so big, so probably there's been an increase.
So you want to Okay, so
I have only one remark apart from the congratulations. So it's really hard to make a ranking between the studies. They are very different type of studies. In all of them, we tasted the flavor of the system engineering, that is the main content of this course. What I mean is that beyond the single details of the various subsystems, we have been able to grab the entire subject with a system engineering level. I propose you a self-assessment. Okay, this is the kind of presentation, good, the professor is excellent, and so on. I propose you a self-assessment because, of course, there is always room for improvement. If you take back your slides and go through them, and you can make a very simple score on these three subjects. All the time you find too many decimal places. Sometimes I've seen 2 tons and 5 grams. This, of course, is a kind of the professor always says this. So every time you find too many decimal places, you put just a minus, and every time you find the rounded numbers, that is what counts, and you put a plus. The second one is the consistency between the different subsystems. So every time you find the same number in mass, in power, across the various subsystems, you put a plus. And the third one is just count how many system slides you have put together, because the system slides are those that are helping very much the audience in following the full rationale of your presentation. So the top level summary, the top level budgets are very much appreciated. And in this slide, of course, an added value is whenever you can provide also a system level ranking of the risks. Again, if you are able to identify in a 1 billion mission the issue of having one very little detail going wrong is negligible at that stage. Okay, I mean the homogeneity in what you are presenting.
Yeah.
With this self-assessment, you make a plus minus. If at the end you have an excess of classes, it's fine.
Yeah, for the risk management, I have to say that is a part that specifically this year has been not covered during the course. So what you saw is just farina de uva. So has been homemade dish. So yeah, so there was no training on that. Look at the system point of view, and then look at the operation point of view, and then look at the integrations and procurement point of view. So there is no time to do everything. So that is why you saw something that is related mostly with peculiar subsystems or hardware, because it's easier, of course, they did this part quite deeply all the course long. So this is
anyway, every item I'm really impressed by the completeness.
So if you want to
any aspect at the stage, of course, of the study, I feel sometimes an imbalance, say, depth of the study, but
and thanks to you to find time for coming, because it's really important for them to have an interface that is not just internal. So there are persons coming from let's say abroad also, and from the scratch looking at the work and being completely out of judgment because of being involved apart from some other again lectures. So this is really definitely important for them to taste where they are, to judge with no say bias, and to appreciate the modeling and the
To my knowledge, in Italy, there are no other courses like this. I mean, there are several other universities, a few other universities where space systems design is taught, but I think this is the only one.
But this is
Not the right one to ask. Let me say, it's a statement, it's not a question. Yeah, I can confirm that there is no other place to find such a
one of these came to me after this.
And for that we have to thank, I mean, she is not here, but we have to thank Professor Pinzi, that was the person that once now we can say several years ago, this kind of course, and now we have more than 30 studies done to be available to be sold to the industry, space value if you want.
The space agency.
Okay. Okay, and thanks again to you and for the guys that I hope enjoy the video. Is that there were other persons that gave support, of course. First of all, Mauro Massari, that is in the rear, that was in charge of the course also. Over here, so Fabio Ferrari, Paolo Lunghi, and I believe also the others, Lorenzo, Daniele, Riccardo, and the other Riccardo. So always available for them. That's it. See you next year.
Le mandiamo le nostre foto.
Ciao, scusami, grazie mille, mi dispiace che sei fino alle 2 l'ultimissima parte. Ci sentiamo poi, ciao.
Vabbè, non è una possibilità. Vabbè, ma oppure può essere diciamo uno schema fisso per tutti, oppure ognuno decide cosa per cosa studiare, nel senso come strutturare il proprio studio, o usi una specie di DRD dove si vada a dividere il sistema. Però ma la struttura